Can everyone on Zoom see the slides okay?
Yeah.
Okay, cool. All right, thank you everyone for coming to the first workshop in the morning here. My name is Jackie, this is Adam, will be your host for today. This is the workshop on benchmarking for robotic manipulation. So just want to give a very quick overview on why we're hosting this workshop and some of the thoughts that we want to be considering today. So one of the things is that benchmarking seems critical for a lot of learning-based fields, especially in manipulation these days, but seems to be a divisive topic. People have very diverse opinions on how we should do benchmarking, why we should do benchmarking. So with this workshop, we really wanted to bring together experts in manipulation, robot learning, embodied AI, sim to real, among many other fields, to really try to think about how should we do benchmarking, and what is the best way for the field to move forward in this area. So we wish to discuss common benchmarks, common metrics, maybe things that we can all agree upon, and perhaps also give constructive feedback to the benchmark that we already have today. Maybe something we can improve on, what are their ups and limitations, and how we can build better benchmarks moving forward. So here's just a long list of questions to sort of get your thoughts started on these topics. First question, do we actually need benchmarking in robot manipulation? Why or why not? When should researchers be disincentivized to benchmark? What's the role of simulators in benchmarking, or should we do all our benchmarks in the real world? There's been a lot of success in benchmarking and large data sets in areas outside of robots, robot manipulation. Can we replicate these successes in robotics as well? How do we standardize data sets when everybody has their own hardware setup, everybody has their own simulation setup, and get results that everybody can share with? What are some quantitative protocols the community can agree on? Which robotic tasks should be benchmarked and maybe should not be benchmarked? And finally, how do we incentivize researchers to benchmark their own learned models so we can all build upon each other's works?
Cool. Thanks, Jackie. As Jackie said, I'm Adam. I'm also one of the co-organizers here. We also have a third co-organizer in person, Sanjana, in the audience. So I'm just going to introduce our speakers for the day. Some are going to be remote, some are going to be in person. So we're going to have Dieter Fox from NVIDIA and the University of Washington. We're going to have Ruzbe from Meta. Abhinav, Ruzbe, how do I say your last name? Okay, Ruzbe Matagi from Meta AI. If I say people's first name only, it's to save myself embarrassment. Then we're going to have Abhinav Gupta from CMU, Maximo Roa from DLR German Aerospace Center, Feifei Li from Stanford, and Lydia Kavraki from Rice. We're also going to have a debate panel, which we're all super excited about. It's going to be moderated by Chelsea Finn from Stanford, and you all can read, so maybe I don't need to read the names of everyone, but we're super excited for that as well. So just to quickly go through the schedule for the day, the talks are going to be more or less in the order that I just said. After the debate, we're going to have a break. The break is scheduled to be 20 minutes, but hopefully we're all having so much fun and the conversation is so spirited that maybe we run a little bit long as possible. So we'll try to keep things on track, but you know, who knows? And we should be finished around lunchtime, around 12:30. So yeah, and that's the schedule. And all the talks, just a reminder to the speakers, when you're presenting, the only live mic in here is this one that I'm speaking into right now. This is also true for the debate panelists. So please, when you're speaking, either speak loudly so that the mic can pick you up, or get close to it. And all the talks will be about 20 minutes, and we'll have 5 minutes for questions at the end. All right. Thank you very much.
So with that said, I will introduce our first speaker, Professor Dieter Fox, who is on Zoom with us today. Dieter is the Senior Director of Robotics at NVIDIA, as well as a professor in the Allen School of Computer Science at the University of Washington. His research interests are in robotics, state estimation, representation learning, among many other areas. Theater has won numerous awards and is a fellow of the AAAI, ACM, IEEE, and recipient of the IEEE RAS Pioneer Award. Theater is also an avid competitive biker in the Seattle area. Please help us welcome Theater.
Oh. All right, I assume that works.
Yep, all looks good.
Jackie, thanks a lot for introduction. Thanks a lot for inviting me. I think this is a super exciting and timely topic, right? We really, as the robotics and learning community, really need to think how we can do benchmarking in robotics. And I'm going to talk kind of coming from a perspective where I fully appreciate, I think, kind of the power and need for deep learning, reinforcement learning for robotics to make progress there. At the same time, I also come from a robotics background where I'm someone who really cares about getting things to work on real robots. And also recently have looked more and more into simulation. And so today I'll talk about how we can maybe leverage simulation to do more benchmarking in robotics for manipulation tasks. That's what I'm going to focus on. First, some high-level statements. I hope these are not, I don't know, overly controversial. We'll see about that. But I think benchmark is just crucial to drive progress in robotics, right? We need to be able to measure how we're doing. I think there's too much work going on in robotics where we just show a little demo at the end of a paper, little experiments, and then try to make very general claims about the capabilities of our techniques. And I think we can clearly learn there from other communities. At the same time, of course, we also all agree that robotics benchmarking is not quite so easy. So it's not just a static data set on which you can do classification. Just because robots are in this interactive setting where they have to physically interact with the environment. And also, we have to be very careful that we design benchmarks such that in light, for example, of deep learning, that they don't lend themselves to easy overfitting to the things that we actually want to measure. On the one hand side, I feel benchmarking on real robot hardware is just very, very hard. There's a huge amount of effort that has to go into this, and I'm sure there's others maybe later in the panel or in the meeting who might not agree with this, but I think it's just very hard to do thorough benchmarking on real hardware because we need to scale it to many different tasks. It's very expensive. Not many kind of teams can, for example, afford to host, for example, let's say a benchmarking system that others can use, and not many research labs can also just afford setting up these benchmarking environments in their own environments. That's why I think kind of a very viable and important way moving forward is looking at simulation, physics-based interactive simulation for benchmarking, where the advantages are, of course, that by having full control over the environment and all the, let's say, almost all of the randomness of these simulators and the scenarios we are setting up, we can really generate kind of the scenarios in which we can do reproducible results, reproducible kind of experimentation, and compare things against each other. Of course, since it's in simulation, it's pretty easy to scale, to test in many scenarios. Another advantage is, of course, also that ground truth information in simulated environment is typically inherently available up to a certain level, depends on what you care about. But we can also use this ground truth information, for example, to generate training data, thinking about machine learning, and also then later to evaluate different techniques. Of course, one big open question is, where do we generate all these assets and tasks that are precise enough so that we can actually do the benchmarking in them? That's an open questions. And also, of course, many tasks that we actually care about, we just can't simulate at this point at sufficient accuracy so that they lend themselves easily for benchmarking. So there's limitations to that, but again, at the same time, I believe that that it's a very promising direction, at least. So here, just quick overview of some of these ongoing or past benchmarking environments and attempts. So there's on the one hand side, benchmarking on real robot systems. There's one that's very well known is, for example, the NIST benchmarks, where they came up with these task boards down here on the left. And these are often then combined with, I think, competitions that typically run at the IROS conference. That's a very well-known benchmarking system. Also, another recent attempt, for example, the tri-finger system is where it's really about benchmarking RL control policies on a real system where people can then just submit their code and it's running on the hardware, which means you can benchmark techniques on a real hardware, but you don't need to maintain the hardware and things like that. There have been other attempts out there doing this. I think one high-level observation is really that it's very hard to convince many people to adopt these benchmarks, simply because if it requires you setting them up in your own environment, then often the burden is just too high. Also, if the benchmark is kind of phrased like a competition at a conference, then also the effort that has to go into it is just extremely high, and many people just are not going to do that, to be honest. Setting up environments like, for example, the tri-finger system or what the OCR TOC system is, where they also provide like benchmarking in the real world. I think it's just a tremendous amount of effort that has to go to host these kind of systems, right? So that others can log in. And it's also not easy to adapt these tasks to new settings and things like that. So there's various caveats if you want to do benchmarking on real robot systems. Now, of course, this being at CoRL, we're all aware of a lot of the benchmarks going on in the what we call embodied AI environments, 3D simulated environments that especially also were driven a lot by the computer vision community. So what's great about is that they are fully interactive 3D simulated environments in which you can train your agents and test them. They have many different tasks. There's a lot of focus also on, for example, visual navigation, higher level planning, and reasoning for manipulation. So the focus here is more on, I would say, visual longer term reasoning rather than low level, let's say, physical interaction. Many of the physical interactions, like really manipulating these things such that it transfers to the real world, is often really abstracted away in these kind of environments. There's other environments that are a bit more focused on the lower level control side. These were developed, I think, mainly also for deep reinforcement learning, testing deep reinforcement learning algorithms. Many of them focus on manipulation skills. I think these are much closer to being actually realistic. So there's really kind of often low-level control involved. There's been good success on transferring results from these environments for locomotion kind of tasks. I think for manipulation, there hasn't been that much effort really showing that if you do well in these environments, that it immediately just transfers to the real world. I think the most recent effort in this domain I like also is HAUS's the many-skill environment here on the lower left that are becoming more and more realistic. At the same time, some of these environments, I think we have to be careful how they are set up. So what we've often observed is, for example, that let's say the camera position, for instance, between train and test set are identical, and the environment is, or the background of the environment is sometimes more or less identical, which of course lends itself really well to overfitting if you have a deep reinforcement learning system. So I think we just need to be careful with these environments to make sure that they have the kind of variability that prevent them from overfitting, so that we can hope that these results really transfer to the real world. I want to talk about some examples, not fully fledged benchmarking examples, but just some areas where I think simulation has been shown to be hopefully sufficiently good that we might be able to transfer these results to the real world. This is, again, more about low-level simulation tasks. compared to the embodied AI tasks, it's kind of, some people might say these are kind of the boring stuff, right? Like about picking up a rigid object. Many people might think that's not really interesting nowadays anymore. But as a roboticist, I must say, if we could solve all these so-called boring tasks, I think it would be really amazing if we had robots that can really do these things really well in the real world. Okay, so I'm going to talk briefly about like grasping of rigid object, motion generation, and then object rearrangement and context-rich industrial tasks. So on benchmarking grasping, this is work especially Clemens and Aditya and Arsalan drove forward, which is using physics simulation for grasping objects. So what they did here was they took, for example, the ShapeNet dataset, almost 9,000 objects from the ShapeNet dataset, as you can see here on the right. And for each object, they tried many, many different random grasps and then fed them, as you can see here on the left, through a physics simulator and use physics simulation in order to figure out whether these grasps are stable or not, meaning that if you move the gripper, whether the object stays within the gripper. So what you can then generate is here, as you see on the right, a data set of objects, and each object is annotated with 2,000 grasps that were deemed to be successful, stable grasp for these objects. Okay, you can use this data set, of course. We've shown that, and I'll give just one brief example for training a grasp system. But I think you can also use this kind of as a first attempt towards benchmarking, where, for example, if you want to benchmark your own technique on that data set, you can, for example, compare the distribution of grasp that your system generates to the distribution of grasp that comes from that annotation. The big assumption here is that if you have a grasp to which there is no nearby grasp in the data set, then it's kind of assumed not to be a successful grasp, right? So we're kind of assuming that these 2,000 grasps kind of cover the whole space of possible grasps of these objects, which is some kind of limitation. And ultimately, I think if we really want to fully benchmark grasping, then we need to do this actually with a physics simulation in the loop, which means you submit a grasp proposal on an object, and then we need to run that through the physics simulator in order to do this. We haven't done that as a service for benchmarking, but I think this would be a next step in order to make this even more powerful. Here's just one example that kind of shows that if you use this data set, this was work that Arsalan did with the grasp network a while ago, that the fact that when you train a deep network on point clouds that are rendered from this data set with grasps, that they actually have a pretty high success rate in the real world, which means somehow that the data set itself has a pretty high quality, I think, with respect to sim-to-real transfer. And I think that is something that we, of course, as roboticists always should care about a lot. Okay. Another area that I think is very important, and I'm really looking forward to Lydia later on sharing her thoughts on this and her progress in that domain, is benchmarking motion generation for manipulation. It's one of the very well-known classical problems for robot manipulation, where you say you have, let's say, a current configuration of the robot, you have an environment that is obstacles, and you have a goal position. The goal position of the robot could be either given in workspace where the gripper should move, but it could also be a goal represented in configuration space. And now you want to generate a path so that the robot gets to that goal position while avoiding collisions with obstacles. And that's, again, it's a big research community that's been working on that for a while. And it's interesting. So we came to this because we realized that, first of all, there are no perfect solutions to this problem out there yet, I would say. But also, it is extremely difficult for someone going into this area to find out which of the existing techniques are actually the ones that you should use in your practical application domain. Because often papers are written where people come up with their own little benchmark system, and then they show experiments where, of course, their technique does better than other techniques. But even though this domain seems very suitable for benchmarking, there has been very little success in, I think, on developing benchmarks that are kind of relevant for real-world applications that we as practitioners might care about, that also, and that cover a wide range of kind of scenarios, actually. There's been some recent work, especially by Lydia Kavrakis' lab, going on Motion Benchmaker, where they developed a system where you can set up different environments for different robot platforms and come up with your own kind of motion planning benchmarking system. The limitations of the time when the paper came out is that I think the variability of these environments isn't that large yet. They also don't really provide a full evaluation protocol, which of course should come with a benchmarking system. And often what is done by the motion planning community is also that they assume, for example, that you have perfect knowledge of the collision and all the objects in the scene, whereas in a realistic setting, you would maybe like to be able to benchmark a system that only uses point cloud observations or something like that, right? So I think there's still work to be done, but there's a little bit of progress at least going on with Lydia's work. Just also as a little bit of a plug for the work that Adam is going to present here at CoRL, and that kind of motivated us to go into this area and to observe the limitations of the benchmarking in this motion generation area, is what we thought. We do a project as follows, where we say, well, we're just going to simulate many different environments. And for these environments, we're then going to use an off-the-shelf motion generation system in simulation, and then do behavior cloning to learn a policy that can replicate this behavior. And by doing that, we just realized again that there is no existing technique out there that just solves these problems, even in simulation, extremely well. But where we are now, you should talk to Adam through a very painful process and long runs on a cluster, is we now generated a data set of these kinds of environments where we procedurally generate the environments and set goal and configurations of the gripper, and then generate more than 3 million demonstrations of how the robot should move between two locations. And then we were able to train a deep network, motion policy networks, MPI-nets, that can take in a point cloud, not perfect collision information, but a point cloud of the environment, and then map that in real time to a motion policy. So you can see here on the right are two examples of these MPI-nets now operating in the real world. So, and this data set will be shared with the community and people can use it. It also comes then with evaluation protocols where we provide the functions for doing collision checkings and all of that to make sure that if you want to test your algorithm, that it doesn't generate collisions and things like that with the environment. Interestingly, just briefly also, just to highlight the need for benchmarking, the process of writing and publishing this paper was pretty painful because we got feedback from reviewers that was very, very inconsistent, right? We actually tested this system also on the benchmaker environment developed by Lydia Kavrakis' lab. And despite that, despite doing all of this, there were results where one reviewer said, oh, this is amazing. I love that you tested it in all these different environments. And someone else just said, oh, I think these tests are way too easy and it's all too simple and I have no idea how this generalizes, right? So I think we just need to keep on working on developing benchmark systems, even for tasks like that, that are kind of accepted by the community as something that if you do really well on these, then that should be something that also works pretty well in the real world. Expanding from just motion generation more to object rearrangement. This is a recent work that Aditya has done, is kind of scene generation. On the left, you see different kind of scenes we can generate procedurally. We can populate them with objects. We can do collision checking in these environments. And you can see that then in these environments, we also can generate rearrangement tasks where you should pick up a certain object, grasp it, move it out of the shelf, for example, and put it at a different location. So, and then the technical details here don't matter, but then, of course, Aditya was able to train a deep network system that is able to do very well on that training data. But that system on the left, we will also publish as a benchmarking environment that people can then use for their own research. So I think this whole space of rearrangement planning is also something where I believe we can do pretty well for benchmarking. Here's now just an example that this then actually translates to success in the real world using point cloud observations. One final example is benchmarking industrial kind of manipulation tasks. This is one of these NIST task boards. The problem with this is, again, it's really hard to do this in the real world. So we thought we would want to do this in simulation. It turns out simulating this is very, very hard and very, very slow because you have these really contact-rich environments. So because in the NVIDIA lab, Yash, he worked with our simulation experts to come up with a simulation system that can now do these contact-rich simulations very fast. So here we can, for example, see we can now simulate 1,000 nut and bolt kind of interactions in real time. And this was before that was not even able. The fastest before that time was actually doing a single nut and bolt at 1/30th of real time. We can now use this to start training reinforcement learning policies in this. And again, we now also published kind of different environments in which people can evaluate and test their reinforcement learning algorithms. So far, our training has been done on state information, which of course does not immediately transfer to the real world. So we're looking into adding touch information as well, so that we can train policies that use touch feedback as well. With that, I want to come to the conclusions. So I think there's been really excellent work on these 3D embodied simulation environments that people can use for both training and benchmarking. A lot of that has been done outside of, let's say, the core robotics community because it serves so well the learning aspects. Sometimes you might say that maybe we're getting almost kind of too many of them because because it might be too easy to set them up in simulation. I think what we need is a bit more benchmarking efforts on these kind of low-level mundane aspects of how to actually control a robot in the real world, like some of the examples I showed you. I think simulation is, of course, a really promising way to move forward with this. There's several caveats, of course. I think we can do this pretty well for object grasping, rearrangement, motion generation, and these contact-rich simulation. We need to make sure that if we set up these benchmarks, that there's enough variety in the tasks, in the assets, in the environment, so that we avoid overfitting, and so that the system can hopefully transfer to the real world. For benchmarking, we need to make sure that even on the test side, simulation should be in the loop itself, so not just labeling, but simulation. And we need to also make sure that this perception is somewhat realistic. I think what would be good is if there was maybe something like a sim to real certificate for benchmark environments, where if you train your system on a benchmark, if there was some notion of how well will the results that you achieve in this environment transfer to the real world. It could be at two levels, where at the one hand side, you could say, if my system does well on this benchmark, then I know that it does well in the real world. Another certificate could be relative, where I say, if my algorithm does better than algorithm B in this benchmark, then I can pretty sure that my algorithm will also do better in the real world than algorithm B, right? So I think we have to think about how to make sure that, again, sim to real is taken into account there. And of course, there's many limitations on simulation, and benchmarking those with the full physics simulation is gonna be hard, but I think it's not impossible. And again, the alternatives are very difficult here. And with that, I'll thank you. Should I stop sharing for Q&A?
Thank you very much, Dieter. We have a couple minutes for questions. If anyone has a question, yeah, Abhinav?
Yeah, thanks, Dieter, for the great talk. I don't know if you can-
I'll repeat it.
Okay.
Yeah. Abhinav says thank you for the great talk.
Thank you.
If there was no issue with the engineering of a real robot benchmark, and if there was no issue with like sharedness of a real robot benchmark, does Dieter believe as a roboticist, a real robot benchmark is always better than a simulated benchmark?
Okay, so tell me if I summarize it incorrectly, but Abhinav is asking if there's no issue with the simulation, like if it's oh, I see. If there's no issue with the engineering for a real robot, do you still think that or do you think that a real robot benchmark would be better than a simulation benchmark? Is that okay? You say it.
Dieter, I'm coming here so that you can.
Hey, Abhinav.
Yeah.
Yeah.
So my question is actually very simple. If there was no constraint on engineering, let's say magically we have thousands of engineers and we have no constraints on building a shared resource like money wise and so on. As a roboticist, do you believe a real robot benchmark will always be better than a simulated benchmark? A very simple question. BC, I think you got it now. Yes.
And of course, you know that wasn't a simple question. Do I believe that? No, actually not quite. So first of all, of course, again, I think it's going to be really important for us to always stay connected to the real robot stuff, right? And make sure that if we do sim benchmarks, that they are connected to real world results, let's say, right? I think there's still advantages, even if we could do it all in the real world, which I just don't believe, because simulating, it's not just a simple benchmarking environment you can set up, right? You need to benchmark many different kinds of environments. So you have to physically set up all these environments and things like that. I think it's going to be extremely hard to thoroughly investigate that. At the same time, I think benchmarking in sim has the advantage that you can do it very quickly, right? You can run maybe 1,000 times real time and scale there to a much larger community that can benchmark their stuff at the same time, and you don't need to share the hardware across all of these efforts.
I mean, I understand that.
I lost my job.
I understand the argument that building new scenes every day in a physical world is hard. I mean, we can debate about it, and I will in my presentation argue against it. But I think what I'm not totally against is like, why do you need speed in a benchmarking? Like you are saying, oh, it could be super real time and so on. I'm not talking about training. I'm talking about benchmarking. In benchmarking, you're just testing in a few environments and so on. So I do agree that simulation has one advantage, which I cannot get in the real world, is the super fast speed. If you have to do thousands of like 1,000 times real world and so on, which you can do by maybe having 1,000 robots in the real world and so on. But assuming that is still, I mean, I'm just trying to understand, is there a real reason why you need 1,000 times faster in benchmarking?
Yeah, no, you're of course right in that respect. I think the risk, let's assume you want to benchmark rearrangement in kitchen environments, right? Simple thing, kind of the rigid object manipulation stuff, rearrangement in a kitchen, and you want to benchmark that in the real world. Now you set up a kitchen in which we can do this. And of course, we all know that what's going to happen is people are going to overfit to that physical instance of the kitchen on which you're benchmarking, right? Now you can hide that kitchen and things like that, but there will always be some overfitting. So in order to avoid that, you need to set up a sufficient number of kitchens that cover sufficient variety so that people can't overfit to it, right? And I think doing this, given the complexity of the whole setup in the real world, is just going to be extremely difficult.
All right, I think we need to move on. Thank you very much, Dieter. Also, because I have the mic, my response to that question is, if you have infinite resources to develop robots, why wouldn't you spend half of infinity on simulation and half of infinity on real robots? And then you could do both. And then you, okay. So anyway, thank you very much, Dieter. So moving on to our next speaker, I think maybe,
Can I?
oh yeah, so you joined the Zoom.
I don't have the Zoom link.
Oh. Yeah, here, I'll give it to you. So it's this. Do you want me, how can I message it to you or email it to you?
Email me.
Okay.
Roosevelt, I just slacked it to you if you have Slack on your.
Okay. All right, so while Roosbe is getting connected, I'll give him an intro. So Roosbe is a research scientist manager at FAIR and or Meta AI, and an affiliate professor at the University of Washington. Prior to joining Meta, he was a research manager at the prior team at the Allen Institute of Artificial Intelligence, and a postdoctoral researcher at the computer science department at Stanford University. Roosbe's research interests are at the intersection of visual learning and embodied AI. So you want to share your screen and then talking.
Okay, cool. Thanks for the introduction. Let me minimize my slides here. Okay. Okay, ideally in embodied AI, okay, so this way. Okay, so ideally in embodied AI, we want our experiments to have these 4 properties. So we want them to be reproducible, diverse, safe, and also, can you speak into the microphone? Oh, okay. And also efficient. So I'm going to talk about each of them in the next few slides to explain what I mean exactly by these. So first, reproducibility. So these are 2 identical robots in 2 different labs, but it's very challenging for example, for lab B to replicate, to reproduce the results of lab A, because the environments, the conditions are totally different from each other. So if I cannot reproduce someone else's results, I cannot measure my progress. I cannot build on top of their what they have built, and so on and so forth. The second property is diversity. So usually when we do robotics experiments, so we are limited to our lab settings. So very simple setup. Usually we put a table in front of the robot to do the experiments, and sometimes we put plain colored cloth on the table to make the perception easier for us. But reality is different. So for in reality, we are faced with such scenes which are visually diverse, visually complex, and very different from our training environments, the lab environments. The other issue is safety. Usually, we don't really want to deploy our models that are not trained well in the real world, and otherwise, such things happen. So we don't really want to damage the environment, damage the robots, and then people that are next to our robot. This thing doesn't work. Okay. So the other property I want to talk about is efficiency. So on the left, you see this video by other groups that they have trained this robot to perform this simple task of opening the door that's placed right in front of the robot. And that took about like 2.5 hours to learn this task. Now imagine a slightly more complex task, like point goal navigation. That the goal is to move towards a point in a room, in a scene. And that required like 2.5 billions of interactions with the scene to learn something meaningful. So what does that mean? It means that if you have 10 robots that are trained simultaneously, it takes 8 years to finish. Okay, so there have been some attempts in the past to come up with benchmarks that address, but they suffer from one or more of these issues that I talked about. So going back to 2007, so DARPA had this project, Learning Applied to Ground Robots. They shipped these robots to different universities and companies, and we trained the robots using our own training data. So this is me, graduate student me, back in 2007, collecting data using this robot. Then we shipped the shipped the flash drive to DARPA, and DARPA did the test for us in their own environment and reported the results back to us. So this had like some issues because the training environments were different, so the comparisons between different teams were not really fair. So I had access to this parking lot in Atlanta, but probably this was not an option for the team in New York. And also, it required a big team of people to run the experiments, to debug the issues and ship the robots and so on and so forth. So it was not really a sustainable effort. Okay, fast forward to 2022, we still don't have good benchmarks for robotics, but there are some interesting efforts in that domain. So one of them is ranking-based robotic benchmark by Abhinav and some of my colleagues at the fair. And so here's the idea. They say, okay, so you run your own algorithms, do local rankings, and send the rankings to us, and we will aggregate these rankings to come up with a global ranking across like different methods. And they also standardize objects and tasks, but still users need to set up the infrastructure, which means that the training data might be different from lab to lab. And that so it means that the ranking might differ significantly based on the training data. So there was another interesting follow-up work that says the title is like train offline, test online. The idea is that, okay, so we will provide you with the offline training data, so you use that data to train your models, and then we will test the models for you. Submit the models, and we will test them for you. So the big challenge here is scaling up the number of tasks. So that if we want to do like a lot of tasks, that would be quite challenging. And so we have to limit ourselves to a few trials for benchmark. And there are similarities between train and test environments, and also offline data is not really a good representative for interactions that happen at the tail of the distribution. We really need to interact with the environment to learn these types of interactions. Okay, some people say let's benchmarks discourage creativity and innovation, so let's ignore them altogether. So I disagree with this statement, because I'm coming from a computer vision background, so these are two main tasks in computer vision: semantic segmentation and object detection. And the x-axis is year, and y-axis is some measure of accuracy. And as you see here, for example, for semantic segmentation, 10 years ago, the performance was like 30%. Now the performance is around like 70%. And there was a lot of creativity and innovation to improve the performance from like 30s to 70s. And yes, so some of the methods are just small increments over the other ones. But overall, there was now it was a good effort. Now they can measure their progress exactly. They know like if how things change and so on and so forth. Okay, so to have reproducible, diverse, efficient, and safe benchmarks, so we propose to use simulators. So simulator. So I'm going to talk about AI2 Thor simulator, simulator that we developed when I was at AI2, and so it has three main components: iThor, RoboThor, and ManipulateThor. iThor is mostly focused on object state changes. For example, here like opening, closing blinds, turning off lights, and also it accurately models the physics of the world. Like for example, here when you open the drawer, the pens roll and so on. The other component of AI2 Thor was RoboThor. So RoboThor addressed the problem of simulation to real transfer. So we wanted to for some reason this doesn't work. Okay. So we wanted to study simulation to real transfer in a in a controlled environment. And so we had some apartments and we made the exact same apartment in simulation. So this is this apartment in simulation. And now it switches to the real world apartment. As you see, they're very similar to each other. So the third part was manipulator. The focus of manipulator was on performing robotic manipulation tasks using robotic arm. So for example, on the left, you see the view of the robot. On the right is a third person camera that here we abstract the way grasping. We focus mostly on planning for manipulation. So using these simulators, we could do several different tasks like navigation, interactive question answering, instruction following, to room rearrangement, and many other tasks in the past couple of years. So to increase the diversity of the scenes, we propose to procedurally generate these scenes. So this work is called Proctor that got Best Paper Award at NeurIPS a few weeks ago. And so here's the idea. So we sample a floor plan, we sample wall layouts and furniture layout and texture and so on to generate new scenes. So this is one of the scenes. I can show you more. So here, so there are different scenes generated by the algorithm. Different number of rooms, different layouts, different textures, and so on and so forth. Just to put this in context, like for example, iGibson environment from Stanford has 15 scenes. Habitat has 90 scenes. A24 has about like 200 scenes. HM3D 1,000 scenes, and so here we sample 10,000 scenes using this framework to train and evaluate our models. So. And annotation comes for free in Proctor because we know what the objects are, we know where they are located, and so on. And also, an interesting point about this framework is that all the objects are interactive, so we can interact with the objects and we can move them around. We can also randomize the material and create for the same scene. We can create like different appearances. Similarly, for lighting randomization, we can change the intensity and the color of the light to simulate the different time of day or different types of lamps and so on and so forth. We can also randomize object location. So it's basically we can randomize objects following certain common sense rules. For example, a chair cannot appear on a stove and those types of rules. So we tested, we trained our models on those 10,000 scenes, tested them for different tasks. One of these tasks was object navigation. The goal is to navigate towards an instance of an object category. And we tested them in two different environments, iThor and also Architector that I didn't talk about. So EMB Clip is a state-of-the-art navigation model. Zero shot means we just train on Proctor data. We do not fine-tune on the train set of these environments. And fine-tuning means we fine-tune for that using the training data provided for that environment. There are two different metrics: success and SPL, which is success weighted by path length and so on. As you see, when we train on Proctor, we see improvements, sometimes like huge improvements for these tasks. We also tested these on environments that are different in terms of appearance, like Robotor and Habitat. So these are very different from Proctor scenes. Still, we see the improvements across these two environments, and that was interesting because this is a scene in Proctor, the synthetic scene. This is a scene in Habitat, like 3D scans of real environments. They're very different from each other in terms of appearance statistics, but still we can generalize to these environments. Similar story for other tasks, like for example, room rearrangement and manipulation. We again saw improvements when we use the models that are trained on diverse data that Proctor generates. And more interestingly, the model was super simple. It just uses uses RGB images as input. We use a clip encoder to encode the images, and there's just a GRU, and we sample from the output of that GRU to output action. So there's no depth, there's no auxiliary losses, no mapping, nothing. It's just this very simple model. Also, so I talked about the diversity of Proctor. Now I'm going to very briefly talk about the recent advances in Habitat. Now we can do 100,000 steps per second. By step, I mean image rendering, physics simulation, and forward-backward passive neural network. Now we can, and the speed up comes from large batch simulation, physics simulation and rendering, and also approximating the physics simulator in a way that doesn't hurt the final performance. And now we can do like 15 billion interactions in just about 2 days. And so now we have these massive speedups as well. Okay, so finally, suggestions for moving forward. I think we should invest more time and money on developing more realistic simulation of the world. And also we should use larger scale compute available to us for fast simulation of the world. For example, our colleagues in computer vision in NLP, they use hundreds of GPUs to train their models. Why not using the same amount of compute to simulate the world around us? Okay, that's it. Thanks.
We have some time for a couple of questions.
So I guess you did something that was really interesting there, where you obviously trained on a large scale simulation data set and stuff. You transferred to Habitat, which I guess is real world. And I guess part of the conference is like, is that last bit expensive or you start to compare approaches? So I guess the root question is like when you look at those other simulated benchmarks, right? So you sort of deployed these other things to generalize to those situations. Did you see the same kind of generalization in Habitat, or was there something fundamentally different? And the reason I'm asking there, right, is if you can sort of show the generalization that others simulated see, right, that gives very strong indication that it would work in the real world. But I guess is that a sufficient kind of measure?
So it really depends on the simulation platform. So if your simulation is a good representative of the real world or the for the task that you're considering, I think that will be some correlation between the simulation performance and real world performance, and then you can hope that so if I improve my models in simulation, they can better generalize to the real world. But if your simulation is not a good representative for that task for real world, probably as we have seen, so I didn't talk about those, but for example, we improved this performance in simulation, but the performance on the real world stays constant, so it doesn't improve. So really depends on the simulator, on the task, and so on. So it cannot be like say one thing that basically covers like all the cases.
But I guess later work you did with the 1,000 scenes, you felt that was sufficient to kind of transfer over to complexity or not?
So that was so because of the diversity, I think it learned a lot of like, for example, the appearance was very diverse from scene to scene, and that helped the model to generalize better. While before that, we used like 100 scenes for training, and 100 scenes is kind of limited in terms of appearance, and we had like problems transferring to a different domain or to the real world because we easily overfit to the data that were available to us. But the diversity, I think, helps the scale. The scale. When we say a scale, we mean diversity. So the scale helps, the diversity helps.
Follow up on the next question here.
diversity in visual representation is something that we've seen in this benchmark. But what about diversity in physicality, like context modeling, slippage, drafting, benchmarking? Where do you think some of the gap is to that? I mean, do we need like 100,000 scenes with different physics, or how do you think you can transfer on physicality side as well as you can do in the So I think these physics and also appearance are not really decoupled from each other. So we should consider both of them together. For example, I want to avoid these obstacles in front of me. So probably I need to have a good visual perception to take actions, and that also basically a combination of appearance and dynamics of the work that influences the actions that I take. It's not just appearance. So I think for that reason, I think we need diversity in both appearance and also in physics simulation, like considering like different dynamics, probably different contact forces and so on. So, but I guess we cannot really disentangle these two. So let's diversify physics simulation and ignore visual appearance, or let's diversify visual appearance and ignore like physics simulation. So for the task that I talked about is mostly focused on navigation. So dynamics does not play like a very important role there. It's mostly like a visual task, but I think in general, we need both of them.
Right. Thank you. I think we'll move on to next speaker. Thank you, Ruzbe. Our next speaker is Professor Abhinav Gupta from Robotics Institute, Carnegie Mellon University, and previously also at Meta AI Research. His research focuses on scaling up robot learning, especially learning in the real world, by building self-supervised, lifelong interactive learning systems. Abhinav is the recipient of many awards, including the Sloan Research Fellowship, Kavli Foundation Grant, Best Student Paper Award, among many others. Please help us welcome Abhinav.
Okay. Thanks for inviting me. Okay, so I think my talk is going to be a little different from the first two talks, because I believe embodiment, or when you call embodied AI, it needs to have a body, and those simulators just don't have a body. It's like so I'm going to talk about more real robotics, and why we need benchmarking with real robots. So I mean, I think this for a couple of first few slides is probably not for this audience. It's mostly for classical robotics people, because whenever I have gone to ICRA and I argued for benchmarking, so I've been trying this for 5-6 years at least since I started doing benchmark. Like my first paper, after that I wanted to say, okay, how do I prove it to everyone else that my first paper works? And I'm coming from computer vision. In computer vision, I one way to prove to people that my thing works, which is benchmark. Whereas in robotics, I never had a benchmark to prove. So I believe my thing works, but I just cannot prove to the world my thing works. And that's what kind of inspired me to start going to ICRA and lots of different conferences in robotics and argue for benchmark. I think this audience, I am assuming, probably already believes benchmarking is critical. So the slides are not that critical here, but at least in ICRA, I've always found much more people are against benchmarking and so on. But still, let's play this game, right? If I show you these three robots, and like I think Ruzbe was kind of, and Peter was pointing out that there are three different environments. They are doing the task of scooping, and I wanted to predict which one works the best. I'll also give you a number that this got 50%, this got 70%, this got 30%. Which one will you choose is the winner? I mean, hopefully all of you are thinking this is such a stupid question to ask, right? I mean, they're all doing different environments. We have no idea what these numbers mean, and so on. Let's try another game, another try of this. And this is something which we are seeing nowadays, a lot of these walking robots, right? I mean, And here is there are two algorithms, which are the most famous algorithms right now. I don't know, maybe there are more famous algorithms, but the two I know of nowadays, I don't work in walking. And I'm showing you these videos. Which one is the better algorithm? This is what currently robotics is, right? We show videos, we say, wow, it works. We show manipulation videos, we say, wow, it works. But then after that, it just stops. And that's why we are not basically seeing this avalanche of papers and one thing and so on, which you see a lot more in computer vision and so on. And so I think if you're a grad student, and I'm assuming a lot of you are grad student or a new faculty, and you are saying, okay, I want to build my career on something which is going to be the hottest thing and so on. And you have to decide which algorithm you want to build on. It's going to be very hard because we don't know if does A work better, B work better, C works better, and so on. Now, to make the matters much worse, let us assume you just chose somehow magically that I want to work on algorithm B because it has more math, and I can add one more loss to the loss function, and that will make it an easy paper. But let's say you choose algorithm B and you start building on it, right? So first, what you'll do is you'll implement your own algorithm on the real robot. As we know, most of the real robotics most of these papers collect their online data. So you have to collect tens of thousands of things. Now you have a problem that you don't have the baseline, right? You don't have the baseline to compare with. So you have to now implement the same baseline on your robot, different baselines on your robot, and then collect data for them. And you keep on doing that. And this leads to the rich get richer problem. And this rich get richer problem is very well known. Labs in Stanford, Berkeley, and my own lab, CMU, maybe have very established setups. We have been publishing papers on those same setups for a long period of time. So we have the baselines already, right? And so if there's a student in my lab, he will say, I know 5 papers that have been published with this same setup. I'll just go there, and it's very easy for me to reproduce the baseline numbers because, and so on. And so that's why the established labs are publishing more and more papers every year, whereas other people that we need, like the democratization that we need, is not happening in this field of robotics. On the other hand, we know the competing story in computer vision and NLP, right? It's just so easy. You just download the data set, right? You run your algorithm if you have it. And to get the baseline numbers, you can just copy the numbers from the table here, essentially. And so if we can bring something like this, that's what we need. And so robotics, I believe, to become successful, we'll need democratization. And to build that democratization, we will need benchmarks. And so this talk, I mean, of course, I hear everyone is probably agreeing with it, but we should do it. The next argument which I hear a lot is vision benchmarks are stupid. Look, and so this is something I hear from ICRA people a lot. They say, look, you vision people have made detection work, but if I use a detector on my robot, it will not work. And I understand vision benchmarks might be stupid. But if we create a robot benchmark, it's our opportunity to fool the vision people to do our benchmarks for us and our job for us. So here's another reason why we should build robot benchmarks, so that we can convince vision people to work on our problem rather than their problem. So benchmarking is just an easy way to scientifically compare algorithms, and that's why we should do it. Now, a good benchmark will have a wide audience that you basically lots and lots of groups can use it, and reproducible. And so Rusbe was saying that simulator is much more reproducible, and reproducibility is critical. I completely agree. And hopefully I'll try to convince you that you can achieve reproducibility in the hardware world as well, essentially. The problem with robotics, and I think this is what everyone has pointed out, like including Dieter, is that because every lab is different, it's just hard to reproduce these numbers. The camera will be different, the hardware will be different, the lighting will be different, and so on. And that is why most of the robotics benchmarks have kind of stayed in this era of very low protocol driven. Like, for example, YCB just gives you a list of 30 objects to work with. Doesn't tell you what task you work on, doesn't tell you how you do the task, doesn't tell you the metric, and so on. And that's why we feel like, oh, this has very low reproducibility. So in hardware world, maybe robotics, maybe benchmark is difficult. This slide I just made because I realized that people are arguing for simulation. So here is my 2 cents on why not simulation, right? So I think the biggest issue, I think, which you are asking, for example, is if you train and test on the same simulator, the learning algorithm is really good. We all know the magic of deep learning. It's going to exploit the simulator issues, some of the problems with the simulator. And now, especially, people are making these approximate bad simulators. It's much more easy to exploit something bad, essentially. And so it feels like you can basically overfit to that badness of the simulator and solve tasks with those things. And interestingly, Dieter, 2 or 3 years ago, when Aditya, who was a student in my lab, was doing his PhD thesis, and Dieter asked a really good question, which kind of took me to the core, right? And Dieter asked me, every year I see these RL papers. The way it happens is that your algorithm is like this. The baseline is always 0. And this is what the graph of every RL paper looks like. The magical thing is, next year, the one which was going like this will become this, the 0. How does this happen? Like if it was working in 2020, getting 80%, how does in 2021 it get 0%? And I thought about it. And in fact, I went back and saw these papers. It's true that a paper which has 80% performance, by next year, it is almost getting 0% performance. Why is that happening? Because people are exploiting these simulators in a bad manner. They overfit to things. And so that's why I feel like this is kind of the core issue with the simulator as well. Then my argument, obviously, again, in real robot versus simulation, and that's what I was trying to ask Dieter essentially here is, if there was no issue, let's start with this problem. If there was no issue in engineering and stuff like that, real robot is always going to be more preferable than simulator. We have to start with this hypothesis. If this hypothesis is not true, then I think we have other issues to discuss essentially. But if hypothesis is true that, okay, real robots is always going to be better because that's what the end task is. So if we can somehow achieve real robots, let's try to get it here. Now, the argument people say real robot is not going to work is because they said real world robots are hard. It takes too much time. I cannot publish 10 papers per year. But if you actually believe in your algorithm, 1 paper a year will give you much more impact than 10 papers a year in simulators, essentially. And you're seeing it actually happening in front of you right now. I can tell you a few algorithms which are actually showing these real world demos, and people are talking about it. Everyone is talking about them and so on. You get much more higher impact. And this is to grad students, by the way. If you are a grad student, you are still debating between simulator and real world. If you show your algorithm on a real world robot working, it's going to get you the maximum impact that you can ever get out of things. And you don't need 10 papers. You just need 1 good paper a year, as everyone says. Then people argued real robot benchmark will not work because it's too much engineering. And here my argument is, we are being kind of I don't want to use the word, but we are having this issue that communities have built much larger shared resources. We know about particle accelerators. We know about shared telescopes and so on. And all we guys cannot agree to just build a shared common robotics cloud, like where thousands of robots just test everyone's algorithm every year. That seems like we don't have the will to do it. To me, it seems a problem of more of a will than engineering issue. If all of us can agree and come together, I'm sure the government will fund it. Governments are funding particle accelerators and all these telescopes, which are much more expensive than building a shared resource of 1,000 robots to test everything out. And so, I mean, it's all feels to me, it's about the, like, for example, Dieter was saying, you had to create different environments and so on. Creating a new home environment is not that hard, right? And in fact, talking about the diversity. So Roosbe will argue that, oh, you should not do real world robot because real world benchmarks or real world training will not be diverse. I argue actually opposite to it. Real world is the most diverse. If you actually want to go every home, you can just start renting 100 per night. You can actually basically get a completely new environment. How much does Roosbe need to do a very good physics environment in a simulator? He will need tens of thousands of dollars before you can get one environment with good physics. I'm not talking about shitty physics where nothing happens daily. I mean, I'm talking about good physics. You will need tens of thousands of dollars before a good environment can be made. Whereas in a real world, everything is open game. Every environment is open game. You can just use it, and that's the new environment that you get out for free. So to me, the diversity argument is actually against simulators rather than for simulators, essentially. So I think the last few minutes, I don't know how many minutes I have left in my argument.
You have like 10 minutes.
10 minutes, okay, good. So the last 10 minutes, I'm going to talk about 2 ways we have been trying to benchmark with the real robot. Again, I mean, we have been trying to convince community. We have been trying to, I feel like I'll keep trying until one of them hits, is the way. So when I'm talking about these papers, you should look at it like this. This was try 1, did not hit. but I still want to tell you about what was try one. Try two, maybe, I mean, it's still in the process of knowing whether it will hit or not. But I mean, we have to keep trying until one other thing hits. And I think that's the way I look at my benchmark research, that I'll keep on trying until everyone picks up one of the things. And this is going to be the success that I was looking for, essentially. So the first try was the result of a workshop that we had. We had a workshop on benchmarking where we invited like lots of people like Sergey, Jitendra, Stephen Charles, and everyone to just discuss about this. It was something like similar, but it was a more closed door workshop. We invited a few people. We made some discussions of what could be a good benchmark and so on. And we came up with this. So there were two resulting output. One was a rearrangement paper that I think that came out of that workshop. And the second one was this, this paper, which is benchmarking with a twist. And the idea is that we agree that recreating. So our first thought was that recreating setup is going to be hard. But even those absolute numbers probably are not meaningful. Like 50%, 60% have no meaning whatsoever. What matters is the relative ranking. Does A algorithm A perform better than B, and so on. So what we can do is we can have somehow magically, if we can evaluate all the algorithms in our own labs, and everyone evaluate the algorithms and send it back to us, we'll get one global algorithm ranking. The beauty of this is, because everyone is trying in their lab, we are getting the diversity of an evaluation automatically by the system. The other good part of it is your local rankings are probably good enough for you publishing the paper, so you still want to do it. Whereas as a community, we are still developing what is going to be the successful thing here as well. And so we basically said the way we are going to look benchmark. So in computer vision, the benchmark is just the data set, the training test plates, and what you are. Here we are going to look at it differently. Here benchmark is going to be not only the training test plates, like the protocols, but also the baseline implementations. So you can download the top 5 results immediately, run them in your lab, and get the result. We are providing you the implementations of the top 5 running algorithms or top 4 running algorithms on this. So you don't have to work hard in implementing your baselines again. And so that was basically our idea, that here are the set of protocols you have to follow. Here are the baselines, the best baseline or state of the art that are running right now on this thing. Now just go and run it and send back the results to us. So it basically became very simple. The way it would run is you basically replicate the best performing, best baselines using them from our website. You run your local experiments, and then you contribute your results to us. And because we'll get results from different labs, we'll get the diversity of evaluation, and we'll basically get some rank out of it, essentially. We had 4 different tasks that we proposed: pouring, scooping, zipping, and insertion. And the idea was you can basically run all these 4 tasks. We gave you the list of objects to buy for training, the list of objects you need to buy for testing, and what locations would you put them to actually evaluate as well. Sorry, there are so many videos, it moves sometimes. Yeah. And so some of the interesting things that we found out was, it turns out that the behavior cloning compared to any offline RL or even closed loop behavior cloning, the open loop behavior cloning works the best. It's still the simplest thing, works the best when it comes to real robots. You can have many complicated papers with simulation results on the best thing, but it turns out the simplest behavior cloning has been the best performer on this real robot task. And the closed loop controllers, even though we can say, closed loop BC is like, I mean, you are taking decision every step of the action, and open is you take the whole trajectory as an output. And so closed loop controllers still remain very, very hard to solve, essentially. Okay, this does not make sense. All right, so then that was the first effort. Immediately after doing it, we realized that it's going to be hard because people still need to do hardware. And our goal was to democratize. We want to have computer vision and ML people also come and do this robotics task for us, essentially. And so, but ML people and computer vision people hate hardware. As soon as you tell them that you do something on hardware, they're like, oh, we'll not do it. So that's why simulator is reigning supreme with them, because it's still software, it's fine, and so on. And so this was a very limited audience. It was not basically catching up because of that. So we went for a next try. Our next try was this, the idea of building a cloud. And this is the kind of resource I feel if we can build as a community, we can actually solve the benchmarking problem. The idea is we are going to build a cloud of tens of thousands of robots. This cloud will basically have, so you can basically do all your experiments. So if you are a lab that cannot afford a robot or you do not want to do hardware, we will do the hardware engineering for you. This provides you the scale of engineering that we need, right? Because one engineer can handle multiple robots, and so this kind of removes the entry barrier. So if you are a computer vision person who's scared to use the hardware because writing drivers is not the thing you want to do and so on, hopefully you can use the robot cloud because we provide you all the things. You upload your algorithm or your data collection procedure. There is live streaming of data. You can see what kind of data it's collecting. You can modify it and re-upload it and so on. So the best thing we've thought about robot cloud, it will remove the entry barrier. Anyone can do robotics from here on because they don't have to worry about the hardware of the robotics. For education, this is going to be amazing. If you think about robotics as a field, only very top tier universities teach it because it's even those universities do not give you any practical, real hands-on experience. By having this kind of a resource, you can have any tier 2 university as well use this resource to teach robotics. We'll basically work with them to create assignments and so on. And in this whole process, because everyone is working at the cloud, it's creating the largest data set, interaction data set that it could create, right? Because every data set has to be, every trajectory that is implemented on the cloud has to be open sourced and so on. So we are starting with this dream of building a cloud. I have to agree that this is very early days. We are still in the process of getting enough people to agree on it and then basically build this as a cloud. But as a first step, to just see if we can get the community interest in it, we propose the first usage of a cloud with Chelsea, Laurel, Peter Abil, and so on, which is the train offline and test online formulation. The idea is that we'll open source an offline data set of interactions to you. You can use this to train. So this is one of the issues with any robotics benchmark, right? Because everyone is training on different data, it's hard to compare. Hopefully by having this open offline data set, now everyone is training on the same data set. So that's the first win we get, which is everyone trains on same data set. So we are comparing apples to apples for the first time. Now you basically train your favorite BC or offline RL. I mean, it's your algorithm to choose from. And you implement it. When you have a policy ready, you send the policy to us. We have the cloud running every 10 days. We run all the policies that we get. We give you a number and we send the number back to you. And in the process, we will basically be knowing which is the best performing algorithm at the end of the day. And all the data that is being created by our thing is also contributing to the open world data set essentially. And so this idea of train offline and test online, we basically started doing it with simple 2 tasks. We said, let's start with 2 tasks and see how, if there's an interest in the community. So we took the task from RB2, which is scooping and pouring, because we think that they are really good tasks for physics as well. And so we basically collected, the way we collected the offline trajectories is via VR teleoperation. We also replayed the trajectories with noise, and sometimes we did state-based BC rollout, because offline RL does not need only expert trajectories, but it also needs some bad trajectories. And so we basically collected a data set with both good and bad trajectories. So our data set looks something like this. So for scooping, we have 1900 trials with 41% teleop, 33% BC, and so on. And pouring, we have around 1000 trials that we have open source essentially. And now the good part is, this is the first also step for us to try to convince vision people to do robotics benchmarks essentially. So the first way we are going to test, the first track that we are testing is, what's a good vision representation for robotics? And so the idea is you upload your own vision representation. We have our ways to train your behavior cloning algorithm using the vision representation, or like offline RL, we can choose whatever policy. And then we will test and tell you back how good your vision algorithm was, how good your visual representation was. And so we tried 5 different representations as a seed to the benchmarking. So 2 in domain that are treated with this very similar data that we have collected, and 3 kind of pre-trained, like trained from ImageNet or trained from Ego4D or whatever. And so these 5 representations are compared against each other. And so these are the 5 representations. BYOL and MoCo trained on similar data, in domain data. And then MoCo, Desert 50 is trained on ImageNet. MoCo is trained on ImageNet as well, and I think this is trained on this is trained on R3M is trained on Ego4D. We basically compare all these different visual representations. So here are some of the results that we are getting in visual, but and then we basically figure out that in-domain data, of course, works better still. We are not getting the transfers from out of domain data that we would like to see, that like we see in computer vision yet. But still, there is hope because out of domain data still seems to work reasonably okay. Not as good as in domain, but still reasonably okay. And the way interface is very simple. All you need to do is you need to provide us these two things, load model and load transform functions. So you provide those functions. And then launch these two scripts, which will train automatically your vision algorithm based policy, and then just send the policy and model to us, and we will evaluate it and give you the number back. So here is your opportunity. If you are a vision person, here's your opportunity to convince the robotics people to use your vision model. We also have a way to compare policy learning. So we are comparing behavior cloning, visual imitation learning, nearest neighbor, IQL, and decision transformers. In this case, we basically chose one representation, vision representation, and we combine it with different policy learning methods and compare the performance. And here are some of the numbers. Again, it turns out that behavior cloning is the most competitive, the simplest behavior cloning. So time after time, whenever we have tried, it is turning out that all the complicated RL and offline RL and other algorithms are still struggling. Behavior cloning is the winner when it comes to real world robots. And to me, that is kind of the biggest thing. In simulators, you can make anything win, but in real world, only the real thing wins. And so I think at the end of the day, so there are these other stuff like, okay, how would you use the vision things and so on? I think if you go to the website, you will be able to do it. Yeah, I want to jump since I might be out of time. All right, so again, the totobenchmark.org, you will be able to download everything to implement your vision model or your policy learning algorithm. And hopefully with this, we can have lots of people doing robotics, a lot more people doing robotics, real robots in real more and more papers, not just simulation. And think people can compare easily, much more easily. I think there are some videos of scooping and so on. And I think with that, I'll end the talk. Okay, I'll be happy to take questions. Yeah, go ahead.
Just a comment on the diversity thing that you mentioned, like rent there may be some. For example, if the host decides not to rent anymore, then you lose like half of your training data or your test data. So that's not a sustainable.
Is that something that does not work for computer vision? I mean, half of the images go out of use from common license, Creative Common license. But is CoCo the thing that made it work? Probably not. I mean, we all can agree that the large scale data sets of computer vision have the same issue and they work fine. So it's all about the scale. At such high scales, some data gets lost, some data gets in. I don't think that can be the issue. To me, I think the bigger question is, what is the definition of diversity in robotics? Are these procedurally generated scenes, which everyone is talking about, is this diverse or is this not diverse? I mean, I don't understand. I mean, someone needs to talk about what is generalization in robotics, what is diversity in robotics. Only then I think we'll be able to better pinpoint what is worth and what is good and what is not good. I mean, I think some of these basic terms which in machine learning seem to be clear, or not machine learning, in other fields seem to be much more developed. Here, I think we are still struggling. What is a generalization? Because I have a lot of times debate about that also. Like, what is a good generalization in a robotics field of robotics as well? Yes.
In fact, copy times are very diverse, but then it also seems to me that your copy on sort of bypass these compounding errors that network in some parts of computation. And also that probably is why it was open to DC and DC. Right? Because if you have much of data in different costs, then right, you will have actually a previous state, and then you will need to have real feedback. Right, so how do you have you ever considered to extend this benchmark to?
No, so I mean, we would love to extend this benchmark, and in fact, I see what you are saying. I mean, you are saying that there are no, I would not say, yeah, so sure. I mean, there are not enough compounding errors because the tasks are easy or something like that is probably what you are claiming. So I mean, I think over a period of time, I agree that maybe there will be some task where this compounding errors and then maybe closed loop will outperform open loop and so on. But at least we will agree that closed loop should not perform worse than the open loop, even in this task, right? I mean, so to me, I think that is, so I mean, what we know for that from here is that closed loop has some issues, maybe with the vision module, because when we are doing state estimation, every step, if some state estimate went wrong, it's basically going to make it the whole thing go wrong. I mean, I don't know. We need to study that more. Task, I mean, we don't want to keep extending task. I mean, I think I'm all in for having as many tasks as possible, somewhere where closed loop will work better than other things. And if you have a task where you think for sure, we'll be happy to try it as well. I mean, we want to keep growing the task. I mean, I think that's an obvious statement. I mean, and it's an easy statement to make, but I mean, it will be hard to do. I agree. I think we have tried everything like LSTM too. I mean, like if you look at some of the other things like decision transformers and stuff like that, they are like, I mean, whatever the state of the art closed loop exists there. I mean, in the field right now, we have the, and in fact, what we were careful was we actually invited the authors themselves to do it so that they don't say that we did a bad implementation. I mean, because I mean, I agree. I mean, it's very hard to implement these things, right? I mean, because everyone has different implementations, different issues. So we want to work with authors. I mean, if you feel your algorithm is there, we want you to get multiple tries to it. If you think, because I think these are the kind of questions we want to answer. Is closed loop going to work better or not? I mean, or is this, I mean, and so, yeah, I mean, if you are interested, if you feel you have a closed loop algorithm, that should be there in the trick. We are happy to work with you and evaluate it.
That's all for this. We will move on to our next segment, which is the debate. I would like to welcome our moderator, Professor Chelsea Finn, and our panelists of the stage, and we will set up some chairs to the left side of the stage.
Just a reminder to the panelists, when you speak, please speak into the microphone, because that's the only way that people on Zoom can hear you. There's no movable mic. So
I will point the mic.
well, maybe we should. I don't know what the right logistical.
Is it possible to move the mic?
Yes.
Yeah, move the mic or have the speakers be closer to the mic at least.
Oh, do those work? Yeah. Oh, okay. Never mind. For me, that's I was supposed to pass. Yeah.
Great. Are we good to get started? Okay. Hi, everyone. I'm Chelsea. I'm assistant professor at Stanford. I work on robot learning, like all of us, and I'll be moderating this debate. So to start off, I'd like to have each of the speakers introduce yourselves and kind of mention your stand or your perspective on benchmarking and robotics.
Hi, I'm Jiajun Wu. I'm also assistant professor at Stanford. My office is one story below Chelsea's. I work on more like computer vision, AI in general, but more like computer vision, but also in the context of how that enable smart, intelligent scene understanding, but also that involves interaction. So yeah, outstanding. Oh well, they asked me for the standing. I said I'm maybe neutral or between neutral and 4. So I think they put me as 4 benchmarking. I think I can talk more, but maybe later, save for later. That's I think there are some specific aspects of benchmarking that would be valuable.
I am Abhinav. I think everyone knows my stand. I just gave a talk, so I think I can move it on.
Hi, I'm Sergey Levin. I'm an associate professor at UC Berkeley. The thing that I think is most important for us to figure out in robotics is how to build very general purpose robotic systems that can generalize broadly in the same way that humans do. And I think a really important consideration in that is to build systems with the right components and be very thoughtful about which of those components could be perfected through benchmarking and which ones require a deeper understanding of the relative trade-offs of different design decisions. So I think my perspective on this is maybe a bit more nuanced in that I don't think that simply getting benchmarking right will be either sufficient or in many cases necessary for us to make the kind of fundamental advance that we need to make right now. And when we think about the role of benchmarks in robotics, we should deploy them very thoughtfully for particular components where it's the right way to make progress, rather than using them indiscriminately in ways that might actually stifle progress.
Great. So I guess kind of Sergey was mentioning like trying to make progress in the field. Maybe we can kind of start off by talking about like, I don't know, how should we go about measuring progress, or are there cases where we don't need to measure progress? Yeah, like, and yeah, what aspects of progress should we be measuring, and how should we measure it? Sergey, do you want to start since you?
Sure. I think it might be helpful for this discussion to think about kind of different types of scientific or engineering progress that have occurred in the past, and how, you know, sometimes you get qualitative changes, sometimes quantitative changes. So I think, you know, it's very tempting to think of progress in robotics kind of analogously to progress on something like the ImageNet benchmark, where it's a fairly narrow, very well scoped task with very particular aims that studies a tiny part of a much bigger problem. But you could imagine, for instance, a very different type of problem. Let's say you're in the beginning of the 20th century and you want to figure out how to build the first powered airplane. Now, I think there it's pretty reasonable to say that, well, building the first powered airplane would not have been made easier if all the airplane builders got together and they were like, okay, what are we going to measure? How long does it take to fly from the East Coast to the West Coast of the United States? How high up can your airplane fly? You know, we've got these balloons that can stay up in the air for hours. Let's have the benchmark be, can you stay in the air for longer than a balloon? Like, you can come up with all these metrics and they all seem like kind of reasonable, but none of them would have helped you build the first powered airplane. In fact, even if you narrow it down into the individual components and you said, well, I want to build a better engine. Okay, like here's like a potential design for like the wings and the tail and so on. Like everyone will slot their engine into this thing and see if their engine works better. That also wouldn't work because the entire system needs to work together. So in a lot of these cases, especially when we're dealing with systems, especially when we're dealing with pushing the boundaries on what that system can do, rather than incrementally improving the degree to which it can do something that's already possible, this question of measurement becomes much more nuanced, and the kind of standard approaches that we're so familiar with, especially from machine learning and vision, aren't as directly applicable.
I think I agree with Sergey that whatever benchmark we'll come up with, it's going to be a bad benchmark. That part I think completely agree. I mean, it's probably not the benchmark that will solve robotics at the end of the day or something like that. But if you think of benchmarking as a monolith, well, probably that's a problem. Benchmarking is an iterative process. It's like something which emerges over time. Today, I can say, okay, I want these 5 qualities to be important, and let's make a benchmark on this. Then we will have someone overfit to, I'm not saying you will overfit. I would say someone will overfit to that benchmark, and you realize, oh man, that was a wrong way of making the benchmark. We should have made a different benchmark or something. And that way the community will adapt and say, okay, this here's a newer benchmark that will emerge and so on. So I mean, in some sense, if it's an iterative process, it actually will help us to figure out the problems in thinking as well. I mean, for me, the issue is that without benchmarks, it's very hard for me as a researcher. So it's not only hard for me as a researcher to decide what to build on, but it's also hard for me as a researcher to show what is bad with your algorithm as well, like and so on. So it's benchmarks provides not just goodness, like, but also like help us figure out the deficiencies of the other algorithm, which might help us to move faster as well. So that was my first point. I mean, and just going back to, because you are listing computer vision and NLP as well. Like if you think of ImageNet, is any of the makers probably not here? But I mean, if you think of the makers of the ImageNet, they actually never envisioned the deep learning. As far as I think, they never envisioned, because it was made in 2009. By 2012 was when the Hinton stuff they came on and so forth. So I mean, in some sense, benchmarks sometimes are not even designed to do those things, and the winner algorithms emerge over time because of those benchmarks themselves. Yeah, so that was.
So the question is, what aspects of the benchmark that's important that we should consider?
Well, measuring progress.
Measuring progress, right? Well, So actually, to me, I feel like specific benchmarks and the progress on that, it may not be that important. And more important is through the collection of building multiple benchmarks, we're actually making progress in the field by not making progress on a specific problem, but actually searching for the right problem that we need to solve. So I feel like what is actually missing, or at least that's not clear. I never feel I'm a core robotics person, but I feel, so a question I have maybe for the robotics people or more robotics people you hear is, so what is the right problem we should solve in robotics? ImageNet, I feel like the most important contribution to it, it had a lot of consequences, but one of the most important contribution, arguably the most important, is not the data set itself. It's actually suggesting that we should focus on this high-level recognition problem on image classification, which we have no clues how to solve, have no ideas how we can do, but that's the right problem to solve instead of 3D reconstruction. So in that sense, robotics, we have been seeing a recent trend, a lot of them led by these people here, Sergey, Chelsea, and Abhinav, and saying, oh, before we were doing 60 pose estimation, those kind of things. So maybe that's not important. We can do more end-to-end. We should think about, just direct manipulation problem. But what is that problem that we should really solve in robotics? Is it grasping? Is it like, door opening? Is it pick and place? Or what is that image classification problem in robotics? That is not totally clear to me. And I feel like how we can use benchmark to measure progress is through we're developing new benchmarks to actually identify the problem. In some sense, I see it as the goal of computation. So what is the goal of robot learning? And I think that would be what benchmark would be able to offer.
Yeah, so maybe we can actually start talking about exactly that question. And I don't think it's going to be any one individual task. I think it's probably going to be more around capabilities. Like, what is the robot capable of doing, or what is the algorithm capable of doing? And maybe Abhinav and Sergey, could you share your thoughts on like, what should those kind of North Stars for robotics look like?
I mean, to me, the way I have been thinking about this, a good benchmark is to have capabilities of a 3-year-old when it comes to the robotic benchmarks. And I talk about, and then there's this two fields that are emerging, right? There's one field which is very much language driven. I mean, right now there's a trend in robotics, there's a language driven robotics field that is emerging, and which assumes that the primitives are there and so on. And then there is other area which is like building primitives, like picking up or like opening or something like that, those kind of primitives. I mean, personally, I feel those are the harder problems, which is building these primitives of task, which a 3-year-old can do, rather than stitching together something. So if I have to make and this is a personal choice here. I mean, I have to say that the good benchmark will be capabilities of a physical manipulation capabilities of a 3-year-old is what basically we should try it as a thing, as a good way of building a benchmark.
I guess it's actually very difficult, I think, to say like, well, what is the capability we should have? I mean, yeah, I think it makes sense to say that robots should have similar capabilities to humans, or at least the similar capabilities to what humans have when they're teleoperating robots. But I think in reality, we also shouldn't understate the difficulty of getting the answer to that question right. Like, I don't think that's a question that we can sit on stage and kind of provide the right answer to off the bat, or at least I can't. Because I think that is actually part of the research problem. And I think, what Jai-Jun said about how, well, like searching for the right problem is actually like kind of part of this whole thing. I think that's actually a really big deal. I want to go back to something that Abhinav mentioned in his talk. He said something like, well, you have like an RL algorithm that is like 80%, and then next year it's like 0% and something else that's better. I haven't seen that. I don't know what that's about, but hypothetically, let's imagine that is the case. That could actually be very, very good. Because what that could actually mean is that people are iterating on the problem. They're saying, okay, well, this year we can solve these problems. Next year, now we can move on to harder problems. And look, all the stuff that was solving the problems before, now it's not good enough. But we can build on it, and we can do better, and we can move on to more complex problems. Like, it's sort of like the dual problem. Instead of hill climbing on the set of problems, you have a hill climbing on the numbers you have for a set of problems. A hill climb on the set you have that you can achieve to some non-trivial degree. It makes sense to think about it that way if you think about your performance on problems as largely binary. And that is actually, I think, very reasonable in robotics. Like, you can say, well, okay, the robot succeeded in like scooping the thingy like 50% of the time. But what does that really mean? Like, that, does it mean that like, it like randomly drops the thing half the time? Well, no, it probably means that it like basically doesn't do it. Like it basically fails. So, we like to put percentages on these things because people expect in science they will have numbers and percentages, but in reality, a lot of these capabilities are more or less binary. And then it makes sense in that case that what you will hill climb on is the set of capabilities that you have. And that's perfectly reasonable. It just doesn't fit us cleanly into the kind of benchmarking that we're used to, for example, in computer vision. But arguably in computer vision, they're also hill climbing on a set of capabilities, because if you correctly classify a larger portion of the images, well, presumably there's some visual concept that you're picking up on that you weren't picking up on before. The same isn't true if we're talking about percentage success rates on robotics tasks.
Cool. So I think this has been a really great discussion so far. Deepak, you can join us as well. And I agree that like basically that we don't really know exactly what the problem is, and part of the research process in robotics is figuring out that problem. And I guess I'd like to push you a little bit more. And my previous question, which you all kind of sidestepped, is like, what are some examples of capabilities that you think are a bottleneck right now that you think we should be evaluating and pushing on?
What task? Robot should?
I'm completely a stateless system right now.
Simple question: what task should robot do? Or what task should be in the benchmark?
Okay, I think like what is challenging right now? I think one big challenge I think we see over and over is generalization, like actually evaluating on test sets and having a training set separate, and then how to do it for robotics is still an open problem. I think I'm on the against side, so I should not say too much on the pro side of this. But like, how do we get robots? What does it even mean to evaluate robots in the open world? Like, how do you list all possible tasks? What is all possible skills? What are all possible environments? And like the learnings we have done over the years through language or vision about benchmarking, what do they even mean in the context of robotics in this robot in the open world scenario?
Any other thoughts, Sergey and Abhinav?
I mean, I think that it is actually genuinely difficult to answer. And the reason it's difficult to answer is because essentially a list of capabilities to some degree presupposes prescribing a kind of a plan for a research agenda. So if I say like, okay, well, maybe we'll figure out like, grasping and pouring today, and we'll figure out like, opening drawers tomorrow and playing basketball the day after and like painting the Mona Lisa the day after that, I'm sort of presupposing that the evolution of general purpose, highly capable robotic learning algorithms will sort of follow a trend where that's the right kind of, I guess for lack of a better word, curriculum for us as researchers. Right. So like, yeah, ultimately, I think what you want is an algorithm that can enable a robot to do anything that a person could do with that same hardware. But in designing, a more fine-grained plan about what those capabilities should be, it's really actually designing a plan for a research project at some very high level. And that's hard. Not that we shouldn't do it, like we should do it. It's just like to get that right, you need to consider, well, what will be your research approach? What kind of methods are you considering? And all those decisions need to go together.
I mean, I think the issue is not what task. I mean, to be frank, I gave the answer that a 3-year-old manipulation capability and so on. I actually feel the issue is, let's just make something. Look, in computer vision, the first, like if you have Jitendra giving a talk, he will talk about, computer vision, the first data set that we had was this contour one. Did contour one create the success of deep learning? Not. Right. So I'm saying that we are going to be wrong in the task that we'll come up with. It will not be the best task that we'll come up with and so on. It's a process. This whole benchmarking thing is a process. I think what we need is a benchmarking thinking, is what I'm arguing here. It's like we need to have a thinking about benchmarking and so on. Again, I want to actually also add on to Sergey's thing. Not everyone needs to do benchmark. When I'm saying robotics needs benchmarks, I'm not saying 100% robotics people should do benchmarking and 100% people, like when everyone was doing COCO and stuff like that, like ROS and timing, they were beating numbers after numbers. I was not doing that. So I was actually on the other side, who was actually gaining from not competing on benchmarking because I could come up with a novel formulation or something like that and so on. Whereas these guys were getting success on this thing and so on. So again, Benchmarking is not something that's going to be right the first time. Benchmarking is not something that is going to, everyone needs to do it, but someone needs to do it. Something needs to happen so that we start talking into like a more, I think it's also about being in a community voice, right? We are missing that community voice right now. Everyone is doing something in their lab and they say, oh, this is the best. Deepak has his own walking thing. He says it is the best. Mark Water has his own walking thing. It says that is the best. I need to know what is best because I want to use one of those algorithms. I don't want to implement all algorithms and then figure out what is the best and so on. So I think it's all about thinking. I mean, and so what I am arguing here is let's start having benchmarking thinking. We will going to be wrong in the good benchmark. It will appear. It will slowly appear into a good. It will appear in a better and better and better benchmark. And who knows? At the end of the day, Sergey, who was not doing benchmark, might solve the problem, and we will be left behind. But it's okay again. I mean, as a community, we will have made a success as well. We need to give both approaches a chance here.
Cool. So I guess on that note, I guess in terms of like a benchmarking mindset, I think that we can essentially think of there being as two different styles of evaluation. One is the benchmarking mindset that we see in computer vision, where evaluation is highly standardized and readily reproducible on usually a pretty diverse data set that covers a very wide range of scenes. But it's also usually using some sort of kind of offline proxy metric for what we might eventually care about, like object detection, like intersection over union or something, given some training data set. And in contrast, robotics papers do include an evaluation. It's just usually on a much smaller scale and in a less standardized way, but also usually on a metric that we care about, like success rate. And so I'm curious, like specifically looking at these two ends of the spectrum. One is the kind of the benchmarking mindset that we see in computer vision, and one is the more smaller scale success rate driven robotics evaluation. Maybe kind of what are the pros and cons? And I guess maybe the two on the left, you can kind of talk about the pros of the first flavor, and Deepak and Sergey, you can talk about the benefits of the second.
Well, okay, I think I've done research in both fields and do both type of evaluations. Okay, so I'm on pro side. Okay, so assuming I'm on the pro side, I can talk about the negatives of the second type of evaluation. Of course, it is using metrics that we care about, like success rate. But at the same time, it is like, you're playing World Cup, but you're the player, you're also the judge, right? So you're like, oh, I've seen this many times. I've been involved in some of these projects I'm doing, and we sometimes do that too. That is, the thing doesn't work well. Yeah, that's okay. We're not comparing with, we're not doing better than a state of art, but there must be a setup, right? Or some setting, like some generalization, some data input constraints and whatever. And we're actually searching for the setups that our method is better than the baselines or the state of the arts. And of course, we'll eventually always find a setup, but that in some sense, you're avoiding the hardest problem that we should really try to solve, because if there's standardized benchmark and people agree that this is something that people care about, and only doing good on this benchmark will get your paper published, then you have this incentive to really try to solve the hard problem instead of avoiding it and try to create a setup like you live in this bubble world that, oh, I'm doing better. And I think in some sense, that's also partially why maybe Abhinav is observing those kind of 2020 algorithm doesn't work in 2021 situation. Of course, there's also benefits on the other side, but I will leave it for Deepak and Sergey.
I mean, to me, the biggest benefit of doing the standardized one is just knowing what works and what doesn't. I mean, right now I feel like there are two things which I ask all the people, okay, does this algorithm work? Does this algorithm does not work? And no one, even in robotics, like if I go and ask a simple question, so I think that's something which I should probably do. I should do a poll with all the experts of robotics and say, does door opening work? Or does bottle opening work? I'm pretty sure that we'll get a very divided answer. Like some people will say, oh, like bottle opening or fridge door opening has been solved 5 years ago and so on. And some people will say, oh, this is not even close to being solved and so on. And I actually have talked to people who have given me both answers. That's why I feel it will not be one common answer. And I think that is the symptomatic problem, right? I mean, that we just don't understand where is robotics today. If I look at the videos of what people are putting under the demonstration, I mean, to me, it seems like we should have robots tomorrow at my home. But clearly that is not happening. So clearly these videos are overfit, like the demo videos that are, or or maybe, I mean, yeah, so I mean, I think that's the whole problem, that I want to understand the demo videos that I see and what is the true state of the art. I mean, I feel there's a big gap between there. And to me, this benchmarking will help me better, will make me trust more. I feel like I don't trust some of these things. You can say, okay, I'm very like I mean, maybe I should improve my outlook and I should just trust everything and so on. But at least right now, I feel like looking at the videos, things should have been solved, but they just don't seem to be solved to me.
Yeah, so I agree with the pros, but I will list some different cons, which I think are very, very serious. So first is, so I have 2 points. First is generalization or benchmarking should not come at the cost of complexity. Like when BSDS was made in Vision in 2000, like for contour detection, it was a really hard problem at that time. And we could figure out benchmarking. Now, suppose that in 2000, you are forcing researchers to work on hand-drawn sketches of cylinders and boxes, which was the case in Vision in 80s. And you are forcing them, no, you should all work on this and you should all evaluate on this. Like that would not be a successful benchmark. Like COCO is a good benchmark because it was complex at the same time it was benchmarked on. In 2014, you cannot ask people to work on contour detection, which was already working very well, like 15 or even foreground background separation, which was working very well in 95. So the difference in machine learning or NLP or vision is that we were able to benchmark things at the same time they were complex for the community to solve. In robotics, it is non-trivial. So if we really want to benchmark in a standardized manner, we have to like scale back all the things to pick and push, like, and things like that, which right now our companies doing that, like covariant, and like you don't want to be working on a setup which you are competing against companies which are trying to make products on. Like nobody will work on making like vacuum or maps for vacuuming, because there is Roomba doing this already. Now, second thing, we should not confuse benchmark for science. Both of them are two different things. Saying that we don't benchmark, so we should not be scientists, that's a wrong thing. Like if we evaluate or compare to a paper, it is our responsibility as scientists and reviewers to as gatekeepers to make sure that the comparisons are done right, and the onus should be on the authors who are publishing as to show that where is their method better and where is that method worse. So that is science part. Benchmarking is one way to do science, but it's not the only way to do science. So we should not confuse, we should not give argument against science as argument for benchmarking, because these two are different and different concepts.
Yeah, I think what I would say here is a little related to that. A while back, actually, quite a while back, about 7-8 years ago, I was on a panel with at a reinforcement learning workshop, the European reinforcement learning workshop with Rich Sutton. And he said something very provocative that got me thinking. He said, well, benchmarking is the lowest form of science. And I thought about that. Well, what does he mean? Like, presumably he's been around for a while. He knows what he's talking about and doesn't just say that lightly. But that doesn't mean that we shouldn't have measurements. What that means is that it's something like this. The purpose of your evaluation, your paper, is not to show that your method is better or worse than all the previous methods. It's to explain the relative merits of different design choices along the different axes that matter for your problem. And it's never going to be the case that whatever you did, let's come back to this product comment that Deepak made. It's never really going to be the case that you just did something that's just like better across the board everywhere. You probably made a bunch of design decisions. The design decisions involve certain trade-offs. They're better for some things and not better for others. You have a hypothesis for why your thing works, and you just show that it really works for that reason. Once you establish that, maybe somebody else can make something work even better for that same reason, even if it's a different method. So all those little dimensions, that's really the important part. That's what your evaluation is supposed to show. The kind of scalar valued thing of whether it's better or worse along some, along its projection onto a vector defined by a benchmark is merely one dimension. And it's not really even the main one in many cases. So I think it's important to keep that in mind. And then you measure these different dimensions, of which standardized benchmarks could be one of them, but it's kind of not the point. Like, if it's a good thing for measuring it, then use it. And if it's not, then use something else.
So one point that Abhinav brought up earlier was that without benchmarks, it's a little bit difficult to tell like what methods out there kind of work best and what you should build on. And I think that the kind of the science arguments that Deepak and Sergey brought up are great kind of in terms of like knowing which design choices are helpful. But in these systems, there are many different design choices and many different things. And so I'm curious what your thoughts are on how to figure out what algorithms to build upon without benchmarks, especially when you're considering papers from different labs.
I'll go out of turn, but I'll be really quick about it. I didn't mean to say which design choices are better. The real question is, what do they do? Because whether they're better or not is dependent on, like, you know, that's like better for what. So the real question is, what do they do? Once you know what they do, then faced with a new problem, you can figure out how to solve that problem. So it's not about whether it's better along different axes. That's not even the question. The question is, what does it do?
Yeah, well, I guess maybe to kind of clarify my question, there are many different kind of design choices, and some of these are kind of thoroughly evaluated in papers, and you kind of see the effect that they have it in the experiments. But there's also design choices that are not often like documented, that have to do with like how something was implemented or coded up. And I think that maybe Abhinav's question before was that how do we know kind of from these different kind of fully coded up systems which ones we should build on to make progress in the community.
She's still continuing.
I can take
Yeah,
another.
this is for Deepak and Sergey, for both of you.
Sure.
He's not happy to answer.
No, we have to, like, I actually meant that, like, we have to know what the parts do. So like, yes, the thing might work due to some esoteric design decision. Like you say, it works because of my brilliant new math, but it actually works because I used 5 layers instead of 4. So that's part of answering, like, what does it do? Like adding a 5th layer does something. The evaluation should evaluate that. And then if someone's faced with a new problem, they might decide, well, this is the kind of problem for which I should add a 5th layer versus use my fancy math. So it really is, like, I really mean that. Like, it's about figuring out, what do the parts do? And, you know, sometimes the parts don't do anything. And that's also, yeah.
I mean, I do want to add on that benchmarks have ablations. Benchmarks have different metrics. They're not any good benchmark is not always one metric. It has a lot. Like, I remember Derek had a paper in 2009 on this whole evaluating the whole sets of object detection failures, like what are different modes of failures and so on. But he still did it on a benchmark. So saying that benchmark will force us to only think about one number is a wrong thing, wrong thinking, because benchmarks can have multiple metrics, multiple ways of evaluating the metrics. And actually people do run ablations on benchmark. I mean, everyone will agree. So we will know what works and what doesn't using a benchmark and so on. I mean, I feel like benchmark is all about comparing 2 different labs. And I feel like if I actually, let's say I was doing walking robot and I just take Deepak's algorithm and I could not recreate the result. And I say 0% performance for Deepak and 90% performance for my algorithm. Will Deepak feel happy? Probably not, right? And he'll say, I did it bad. Now I'll say, oh, I tried my best to do it. You know, this is my best possible implementation. You can come and you can do it as well and so on. To me, I want to understand what is the failure of an algorithm and what is the failure of an environment, or there are these different ways things can fail, right? It could be failure of an algorithm or it could be failure of an environment. And those things can only emerge when we standardize a little bit more. Again, I do want to emphasize, I mean, maybe it's a cop-out in some sense, but I mean, I'm not arguing that everyone should do benchmark. I'm arguing some of the people should definitely do benchmark so that we have some things emerging and so on and so forth. But I mean, there will always be people who will not follow the benchmark, who will make their own way and so on, which is good, which is exactly how the science should be. And going on to Deepak's argument of science, I agree that benchmarking and science is not the same, but the best way to succeed science is have multiple ways of doing it, not put all eggs on not benchmarking basket. And so to me, it's all about, let's at least have some benchmark. Why are we so scared to create a benchmark? To me, it seems like something is wrong with our community that we are so scared to create a benchmark. Is it like all our hidden secrets will come out? No, probably it's something like that is what I feel like. We should just go for it. We should just create the benchmark. It's okay if things will fail, if your paper will show that it has actually 0% performance. That happens, right? I mean, because you did it on your year and in your environment, and whereas in benchmark it's not working and so on. It should also not mean that your algorithm will not work in some other setting. What we know is, under these settings, this algorithm is failing, and we are comparing multiple algorithms under these settings, and that's it. It doesn't say anything more than that, essentially. And I think, I mean, again, benchmarks will change. I mean, this is what I want to, again, add on at the end.
Also, in some sense, Sergey, you're saying, oh, it's not like if having a benchmark is forcing anyone to use that benchmark, right? For example, ImageNet, no one forces to use it. And the reason that people start to use ImageNet is because they find out that this is the real thing in the sense that if you make it work, it can also work in other scenarios, right? So, for example, when I was a student, I trained models on ImageNet and then tested pre-trained model and tested some images that are totally different, like line joins or something that may not even exist in ImageNet. It still works and it still sort of generalizes and helps. So if people find that the benchmark is so well built in the sense that, or maybe that's an accident, but anyway, it is so useful in the sense that, any progress there can directly lead to practical impact. Eventually, people will start to adopt it, and people find like, okay, only by making progress there will lead to the highest impact. And so that's why it is like a natural selection. So it's not like, the good benchmarks, they also survive. And also, I feel like there's another point that is people are arguing that a lot of things we should care about, like there's generalization, there's robustness, there's all these things that we should care about. So building a benchmark, we have to consider all these things. But maybe that's also because we don't really have the right benchmark, or maybe it's, again, going back to earlier what I said, it's like we don't really have the right problem to solve. So think about it again. We're going back to the problem of ImageNet, right? Why is classification the right problem to solve? And also, if you look at ImageNet data set, to many extent, it's still not being fully utilized. ImageNet has hierarchy that no one has been really using it. Maybe it is something that's not going to be useful, but when they build it, they actually put a lot of effort and hope on the hierarchical structure of the ontology of the categories will be useful. But also, ImageNet has a lot of human labels that are not totally correct. So there's a kind of the distribution. And I think recently, for example, people have shown that if you train with these human labels with errors, that actually improves the robustness of the method. So in more importantly, again, going back to what I said earlier, ImageNet really helps you to generalize just by solving this classification problem. So if we can find that right problem in robotics, that, okay, just by solving this problem, right, with the right benchmark, we'll be able to generalize to solve other problems in robotics. And also, hopefully, the system will be robust as well. And I think that would be great if possible.
Actually, one of the reasons why we need benchmark, I mean, I remember a very good story, and maybe that it will create a lighter element to this whole thing. One of the reasons we need benchmark is to stop people like me, right? I mean, so for example, we were having a dinner with Alusha and Deepak. And Deepak, I know hopefully all of you guys have seen the walking robot of Deepak and so on, right? And so we started having argument of how good it works and so on. And I started telling Deepak, look, your student was saying this, and that is why I believe it doesn't generalize and so on and so on. And Deepak got upset. He said, oh, that is completely wrong characterization of it. If Deepak had done it on a benchmark, I would have not been able to say anything because I know under what setting it was evaluated, under what setting it was. So people like me can go out and, I mean, all I'm saying is it's very easy for me to go and say, Sergey's algorithm doesn't work because he made that trick in the simulation which made it work. And I've heard this a lot of time that there was that simulator, they tricked it somehow to make it work and so on. Benchmark will stop these kind of arguments as well. So if you guys just are ready to benchmarks just to stop me, I think we should do it. I mean, we should just do benchmark. There's just no reason not to do it, I feel. Do you agree, by the way? I will not be criticizing your opinion.
Yeah.
I've heard both sides about your work.
Yes.
No.
Okay. I think so. I come from vision background and I work in robotics, right? I don't think this is true that robotics people are scared of benchmark and vision people are fearless. Like that's a little bit narcissistic. And I am both the communities. I think the main thing is we should not treat absence of evidence as evidence of absence, right? There is no benchmark does not mean that robotics people are scared of benchmark. There is no benchmark for a good reason, because we do not know how to make a benchmark. Right, that is the main deal. Like at robots, for instance, since they have a talk right now. If you run a regular robot for 10 minutes, motors heat up and they change behavior. Like in the same lab, same robot changes behavior. Like robot falls, camera moves a little bit. Now it's a different robot because it's like your eyes have moved. Now you take time to adapt. So benchmarking, even for a single system within the lab, is very difficult. Now try thinking of this across scale and across labs. Like Unitary, the robot we use is here. Every robot they send us is different. Like every robot, like we order the same robot, A1, Go1, every robot they send is different. Like it's not like we do not want benchmarks. It's more like, how do we do it? Now the way to do benchmark is not to make MNIST of robotics and say, oh, let's first solve MNIST in benchmark setting, because that doesn't serve a purpose. Like if today I force you in Vision to work on MNIST for the sake of benchmark, how many people will really work on MNIST? Like if we really like, maybe like 0.01% of the community will work on MNIST in Vision today for classification if Imagen was not existed. So this is the state. I think we should not like say that benchmark does not exist, so we are scared. It's just the absence of evidence is not evidence of absence.
I think this is a really good point, and something that kind of builds on this is that, well, benchmarking, I think, works really well if you can have a very cleanly delineated problem with very clean abstractions that you can evaluate in isolation. And the problem is that in robotics, if you want a real world robotic evaluation, necessarily what you're really evaluating is a system. And there's a little bit of incongruence here, because typically we'll be making a claim about a method. Like I say, okay, I have a better neural net architecture, or I have a better imitation learning algorithm. But then what you're evaluating is a system that involves that novel methodological idea in the context of a bunch of other stuff. Like that example I made with the airplane before, like you swap out different engines, you think you're benchmarking engines, but no, you're actually benchmarking the system and how that engine fits into that system. And this is where we get into trouble, where you say like, oh, your method doesn't work when I take off that special piece of tape that you had on the finger. It's like, well, yeah, but who cares? Because my method just had to embed it in some system that would abstract away all the other stuff. Like someone else can figure out how to deal with the other parts. And we need that abstraction. We need to, you know, to make scientific progress, we have to specialize, we have to solve parts separately. So this is where we get in trouble. And just to keep this short, the point I want to make here is that benchmarking works really, really well when you can isolate something. Like, for example, in 2020, in my group, we started doing a lot of work on offline reinforcement learning. We built a benchmark for a very, very specific purpose, to benchmark offline reinforcement learning algorithms. It was not intended to see whether offline reinforcement learning algorithms are better or worse than something else. It was just literally like benchmark the different offline algorithms. And it served that purpose. And it didn't serve any other purpose, nor should it have been used for any other purpose. So I think that's how we can deploy benchmarks very strategically to really advance science. But it takes a lot of careful thought, because when you do that, you're presuming that that's the right way to chop up the problem. So you have to get that right. And that's why it's not easy.
So what I am hearing, and I think this is a good thing, is you guys agree that we should do a benchmark. You're just saying that it's just hard to do a benchmark. Is that clear? Is that a fair statement?
I mean, we are put arbitrarily into two groups. So we do agree that benchmarking is important. It's the most things like how to do it. Like for instance, because suppose you have to assemble a GPU every time you want to show your ImageNet system. And in one GPU, you put one screw very loose, and now you say my performance is lower.
To me, actually, I mean, I feel like if you even agree that we need to do benchmark, it's just that hard. I understand, and I, like in my whole slides, I was saying 100 times that robotics benchmarking is hard, what is benchmarking is hard, and I agree for. So all I need is one simple commitment from 10 people in top 10 people in the world, that if we come up with a benchmark where you are happy with, and we will make it maybe very specific, maybe whatever, you commit to having at least 2 papers a year on that benchmark. I think that should just, all I need is a activation energy for a benchmark. I feel like robotics misses the activation energy. Once we get Sergey to have 2 papers every year, you to have 2 papers every year, you to have 2 papers on that benchmark, the rest of the people will be forced to do that. By force, I mean, they will feel the urge to do it. They will feel the force is the wrong word. I got it immediately as soon as I said it. So I'm taking back the force. What I'm saying, you will feel inspired to do it as well. Inspired is a better word.
A really short pot shot at that comment. I think another way to rephrase what you said about benchmarking being hard is making a benchmark that is bad is easy. And I think we should be conscious of that counterpoint. Like one way to say it is making a benchmark is hard. The other way to say it is making a bad benchmark is easy. And that we should be very wary of that.
No, yeah, and we don't want to agree beforehand. What if it's a bad, like the bad easy word?
No, I have been saying it from the beginning that we are going to make a bad benchmark, but it will improve itself. That's the beauty of this whole system. It's an iterative process. It will improve because we will, as a community, realize that it's a bad benchmark, but we have a benchmarking thinking. So someone will say, I want to create ImageNet. Someone will say, I want to create a CoCo. Someone will say, because that is a much better thing. And I think what I feel is we need an activation energy and just a little bit change in thinking, and I think it will happen.
Well, if it's a bad benchmark, there's no way to ask Sergey and Deepak sacrifice for your bad benchmark by forcing them to publish 2 papers per year on that benchmark.
Remember, I started with the hypothesis that I will make up a benchmark at least you guys are happy with for some very specific problem. In that case, you have to give me two papers a year. That's it. Because you said that you are happy with that aspect of the benchmark, and that's why I'm asking two papers, two papers per year. I'm being very careful in my words or choice, because I feel like right now the problem is you can come up with benchmark, but the first paper of the benchmark will be the only paper that has used as benchmark, but nothing else. Yeah, I don't think. Yeah.
How much time do we have? 10 minutes.
Should we
Okay.
do some
There
audience?
are a couple audience questions. We'll start with Dorsa and then we'll go to Bakash. I can repeat your question.
Okay, so yeah, great conversation. I think one problem that we have right now with benchmarks is we say opening a drawer is like the thing that you're going to, but that's an example of a bad benchmark, because when you just say opening a drawer, right, like you can use whatever method you want for opening the drawer. So the question is, what is hard in robotics? The thing that is hard in robotics is generalization. So we need to have a benchmark for generalization. So the question that I have is, how can we go after a benchmark when we are looking at the task of generalization as the thing that you're trying to assess? And that kind of like helps, because individually, like as Sergey was saying, like if you're talking about individual tasks of imitation learning algorithm, it's really hard to assess that individually. But the big thing, the system thing that you want to assess is generalization. So how should you come?
This is the beauty of the benchmark, actually. I mean, you are actually telling me the beauty of the benchmark. So if you remember, the way computer vision will do it is they will create 4 instances of opening a drawer, and then someone will find a way to hack that problem, like you were saying, and you'll say, oh, this is not the solution. So now what will happen is someone will say, okay, that is not the solution. So the real benchmark should have been mostly like transferring from opening, let's say, a door to a drawer. I'm just coming up with something.
Tasks, we should do better on K+1, and like we don't know how to choose K+1, and that is like
I mean, that is the same problem as we don't know how to choose 10 categories to classify on. I mean, sure, the 10 categories are not going to be the best 10 categories we should have done it on, but there are some 10 categories. Again, I feel like by actually having you all work on the opening a drawer, I will know what are the ways to hack it and what are the ways I can make it a more generic problem so that it cannot be hacked as well. I again feel like it's an iterative process. If we think that there's going to be the one monolith benchmark, that I think is I mean, I agree, it's a failure. So that.
It's like the question, what are the assumptions under which you're.
Right, I mean, so initially, that's the, I mean, so and I think that's what Yajan was saying, maybe it did not come out clear, is benchmarks will also force us to think about generalization problem. I actually, one of the points I made in my talk is, when I talk to about generalization to different people in robotics, they don't agree on what is a generalization in robotics even. If we cannot agree on what is a definition of generalization in robotics, we have bigger issues, and benchmark will help us to even have some common agreement but all I'm saying is that somehow not everyone will have to adhere to that common agreement of generalization, because when everyone was doing classification on ImageNet or something like that, I mean, there are people who are saying this is not the real problem. The real problem is few shot, not when you can have 1 million images and so on and so forth. There will always be standouts like that, and those are good. Those standouts will help to change the field also as well. I mean, in some sense.
Do you have something to add?
Yeah. One thing is with the benchmarks, it seems like you just go in straight to evaluation phase. But kind of with all robots, them as a system, there's a calibration phase. And, you know, yes, you fell over, yes, your camera's slightly off, yes, you don't have the thing on your tape. And then like basically every setup, if you run an evaluation in your lab, is you'll have a whole period to calibrate the robot. And then you'll run the evaluation phase. And when I see the benchmarks come out, it's like, nope, straight to evaluation, no calibration. And it seems like like when we talk about generalization, we're missing an entire phase where it's like, hey, I can actually try my algorithm, I can do my coordination, I can get my patterns, whatever it is to calibrate.
I mean, I think that calibration step is also okay, I'm trying to find the right way to say it because it could be wrong. This calibration step is actually sometimes the culprit as well. So I agree that there should be a calibration step, but this calibration step should also be agreed on by the whole community. Like, what is a good calibration step that we are going to allow? Because right now I feel what happens in a calibration step is you figure out where algorithm works and you does not, and you change your, and I'm not saying you do it, I'm just saying at least some people is doing it at the calibration step. They figure out that if they keep the box right like this, the algorithm will work. So they will only test it in this condition, because the hand can reach exactly up to this there. And then once it has reached here, it has to come back. So it will basically, I have seen these examples of people opening doors and drawers where it's just opening the drawer because it was at the right location at the right time and it was doing the right motion at the right time. This is what benchmark would stop. Like you manufacturing your own environment to show your algorithm video working, essentially.
So there is a pattern here. Everybody asks a question about a benchmark and you say it's an open problem. Like that's the whole problem. Like everything about benchmark is an open problem right now. Like what task, open problem. What assumptions, open problem. What environments, open problem. What robots, open problem. How long to run the robot, open problem. Like this is a series of open problems. And this is what is the difficulty. And we have to understand, we cannot compare robotics to vision directly. Suppose every time you have to submit your result to ImageNet, and you have to worry about, oh, which GPU are they running on? Is it NVIDIA 3090, 3080? Oh, do they have driver correctly? Oh, and suddenly we had 0% accuracy because driver failed. Like we have NVIDIA making this layer on top of GPUs for everyone to not worry about. Like we do not care about where you run your code. Like you don't care about how your machine was assembled. Like was it shaking? Was the fan running, making noise? All these things are abstracted away. And all these cause open problems in robotics, which is what makes benchmark difficult. So
no, I agree. I'm coping out by saying open problem, but I mean, I am giving a solution. I don't want you to look at that solution and say that this is what you should do. So that's why today in this room in front of 50 people, all I want is a commitment to say, if you agree with the benchmark, let's find 6 people who have big research groups, and I want big research groups, sorry. I mean, I'm being biased, but it is a good way to activate is what I reason. So all I want is 6 big research groups, simple commitment that if 6 of us sit together and come up with this, we commit to 2 papers per year on that thing. And I'm not nothing else. So we will sit together, we will talk for 1 year, maybe, and such that we will have at least 6 of us can agree. If 6 of us cannot agree, then we know that there is no solution to it forever. I mean, and then I will keep trying until something hits. I'm not going to give up my trials, but I will, yeah.
Cool. Let's go to Vikash for the last question.
Let me say one sentence. That's okay. Well, I feel like the reason that people don't want to commit is because first people agree that it's important and we want to work on it, and there should be people like you who keep pushing for benchmarks. But at the same time, they may feel like it's not ready to be used in next year or something. So it's kind of crazy to commit to say we do 2 papers per year on your benchmark. It may take another 10 years or something.
Benchmark, it will be our benchmark. I mean, benchmark is not for it's benchmark by the robotics community for the robotics community. It's like, again, that's actually.
But then that goes back to the situation that everyone's saying, oh, your benchmark is not good enough. So actually, every paper I publish, I'm creating my setup. So in that sense, I'm creating my own mini benchmark, and I am publishing 2 papers on my own mini benchmark. I'm just not using your benchmark.
No, so that's why I'm saying we need some setup. There are 5 universities can agree that they are a good setup for at least some problems.
But then I feel like that may take another 10 years for the agreement to be reached.
Let's go to Vikash. We should, yeah.
Sorry.
Yeah, so point number 1. It seems like at some level, everyone is agreeing that there should be a benchmark. But really the level of disagreement is, can you find the right one or not? And if we find this, it's a great idea. If we can't find it, can you see by using that benchmark? Right? But like the nuances in every kind of answers that I heard was, it will be different if it was a simulation benchmark versus actually the concept, a real world robot benchmark. Because the systems aspect can be abstracted away if it was a simulation benchmark. So I don't know if there is time, if you want to comment on that, that will be important if people want to do a simulation.
I think if it's simulation, it should be benchmark. I think nobody can be against benchmark in simulation. But I think we're talking about robot and real robot scenarios. Like Sergey already has his D4RL on simulation in there, and whatever. Like you can, yeah. If you really do not want to make benchmark in simulation, then I think it's an excuse. I agree, but there are actually open problems in robotics, like in the hardware part when you have a system to do.
Do you agree? Sorry, I mean, going back to Vikash's question, what is the simulation benchmark you use for manipulation? If there is something, I mean, I don't think even there is an agreement there as well.
Well, I guess
because there is a simulator from AI to Thor, there's a simulator from Facebook, there's a simulator from NVIDIA, there's a simulator from this. I don't think we agree. I mean, while I love to have
no, I think it's the time. So let me just cut it off here, because the simulators are finally getting to a stage where you can talk about benchmarks. So for instance, like Isaac Sim, it's very fast. Like having a manipulation high vision benchmark in simulation was extremely slow and painful to simulate.
I think I had a question with Deepa. Fastness has nothing to do with benchmarking.
But you
benchmarking, you don't, I'm not talking training. that's another issue. I mean, like you don't have to train on the same simulator to test on the same simulator as well. You can go and get your policy from whatever. I will test it on this simulator. It is not fast, but it is so good in realism that this is. So in fact, I should say we do not want a fast model. If it is as fast as and as good as the best one, then it's fine. But what we do not care about is fast when it comes to benchmarking. We care about realism much more.
Okay, this is again a vision and language bias. Vision and language committee got lucky because people click photos. You go to Eiffel Tower, there are 1,000 photos of Eiffel Tower. If you go there, you'll click another photo with you in there, right? So data exists for vision out there because mobile phones came earlier. For language, people love to write. People love to explain others on CoRL what life means. So you can read from that. But for robotics, if you don't allow training or data, like where do I train?
No, but what if, I mean, I'm asking a scenario that Vikash makes up a new simulator, which is running 1 frame per minute, which is the worst. Like, I mean, I don't know what is very bad. And Isaac Jim is running 10,000 frames per day. It's okay to train an Isaac Jim, but test it on Vikash because Vikash's simulator is so good that it has a simulation certificate.
I think this is okay, but the problem is right now in Isaac Jim, it just got released this year. So there are people already making benchmarks for
speed is not the issue.
Environment. For training it is.
No, but why do you have
for evaluation? It's fine, but if you don't have a method,
we need to wrap up. Well, I'll have one more. I think Sergey was going to say something on the real robot stuff, so he can have the final word here.
Oh, okay. I was actually going to briefly respond to a tiny part of what Vikash said, but what I was going to say is that I think like one amendment I would make to what you said is I don't think we need one benchmark. I actually think the right way to think about benchmarks is the same way that we think about claims in a paper. Like there's some kind of question that it's supposed to be asking, like, you know, it's testing along some dimension, and that, you know, needs to be narrowly scoped. There needs to be some kind of purpose to it. And probably if you're evaluating a system, you probably need to evaluate along multiple axes. So I really don't think we should be thinking of like, what is like the one ultimate benchmark for, let's say, robotic manipulation. I think we should be thinking about how do we test things that we, you know, want to understand about methods.
Cool. I think that's a good note to end on. Let's thank our debaters or panelists.
I'll just make one disclaimer. I'm also co-author on the paper with Abhinav on that benchmarking thing. So I'm not totally against it.
Okay, great. Hi, everyone. Welcome back after the break to our benchmarking robot manipulation workshop. Our next speaker is Dr. Maximo Roa. He's a group leader on robotic planning and manipulation at the Institute of Robotics and Mechatronics at DLR, German Aerospace Center. In the past, he also joined Roboception, a DLR spin-off working on 3D perception solutions for robotics as a senior expert on grasping and manipulation. Dr. Roa obtained his PhD in robotics in 2009 at the Polytechnical University of Catalonia. Please help me welcome Dr. Maximo Roa.
Thank you.
Maximo, just one quick thing. Could you turn on the live transcript when you speak on your slide?
Oh, I think it's on already.
Okay. If it's on already, that's good. Okay. Thank you. Thank you.
It's on already.
Okay.
Okay, good. So, hello, everyone. Good to see you. It's a bit late here in Germany, 11 p.m., but I hope you're having a wonderful day over there in New Zealand. So let me share my screen. I hope you can see now the presentation. Please tell me if that's the case. Yes, I guess. You're looking at the slides right now, right?
Yeah. Yeah. Okay. Yep, slides are good.
Okay, good. So let's get started. I'm sorry, I will turn off my camera. Turns out that I had an internet breakdown now, and I'm connected via my mobile phone. So I will stop my video in the meantime, but I'll turn it on again for the questions. So let's get started. Basically, I want to talk to you today about the application of benchmark protocols, different benchmark protocols to the design of the clash hand that we have developed at the Institute of Robotics and Mechatronics and DLR. So let me start by mentioning something about the ways that we have for measuring the performance of robotic manipulation systems. So basically, establishing some experimentation methodologies to compare results across different groups is still a challenge that we have in robotics. And for testing the advances, we usually rely on competitions and benchmarks. And this table compares basically some aspects of both of them. So competitions, for instance, provide a fixed set of rules and in most cases some predefined tasks and expect solutions that solve the challenge in an efficient way. So the risk that we have with competitions basically is that some teams can over-engineer the solutions to solve the desired task. And this, of course, limits the applicability of the methods outside the scope of the competition. On benchmarks, on the other hand, we usually have established procedures for testing different aspects of robotic manipulation. And the idea is to guarantee repeatability and reproducibility of the results. These benchmarks in general can be executed anytime, and the results are evaluated either by the team or by some judge, but following an established protocol. Here, this is a table that we published on a paper on RAL last year, which summarizes some of the existing competitions that involve robotic manipulation in some way. Most of them actually, if you see, they use a fixed set of tasks for the competition design. And well, this has the advantage that it allows to create interesting scenarios that enable the progress to be measured objectively based on the task performance. So competitions are crucial to the community, in my opinion, and some of them actually we know have been very influential for developing certain applications, for instance, in logistics scenarios. Benchmarks now, in terms of robotic manipulations, can be classified in these three different levels. So I introduce here the mechanism level, where we have measures that benchmarks that measure the intrinsic capability of the mechanisms, mainly the hand or the gripper. We can measure, for instance, robustness and resilience of the hands or mechanical properties, such as fingertip force or gripping force. At the algorithmic level, we can evaluate a specific part of the manipulation pipeline. For instance, the grasp planning stage, the motion planning for the full arm, or the object recognition and pose estimation. But in most cases, we are interested in things at the system level. So that means considering the performance of the robotic system as a whole, solving autonomously certain tasks, such as the box and block test, or picking up place in certain objects in logistic scenarios, or picking from shelves. And a nice summary of a lot of benchmarks that were proposed for manipulation is summarized on the special issue in 2021 on robotic manipulation. So this is a collection of 14 different benchmarks, for instance, for bi-manual manipulation, in-hand manipulation, or grasp planning algorithms. And of course, I encourage you to take a look to these papers and see how can you use these benchmarks to measure the progress in your research. But today, I wanted to present to you how we use benchmarks for the evolution of the design of the clash hand. So let me start by showing this video. This is an example of the ideas that we had in this project, SOMA. SOMA stands for soft manipulation. So we work with different partners, mainly with Ocado Technologies in the UK. And the idea was to develop an N effector that could exploit what we call environmental constraints. That means explicitly exploiting contacts with the environment to guide the manipulation actions or to grasp difficult objects. In this slide, for instance, we see two of these constraints. The one that you are looking at right now is what we call the wall grasp, meaning that we basically push the object against the side of the container to be able to grasp the punnet in this case. And here on the right side, we have what we call the edge grasp. So for grasping such a thin object like this ticket or a business card, the hand basically slides the object towards one of the edges and then grasps the ticket. Good. So this was a couple of examples of the application of the clash hand. Let me show you quickly how the hand is constructed. So clash stands for compliant, low-cost, antagonistic servo hand. The design follows the idea of embedding variable stiffness actuation into a robotic end effector. So to enable this, we created these two modules that you see here on the left and the right column. This is a module for 2 fingers, so for parallel fingers, and then there is another module that we call the thumb. Each module has 4 motors. 3 of them are used for, well, changing the flexion and extension or the abduction adduction degrees of freedom. And 1 of them is used for changing the pretension of the tendons, which basically changes the joint stiffness and allows the fingers to be very soft or very stiff, depending on the application. Now, here you see how this variable stiffness is implemented with what we call the flexible antagonistic spring or FAS system. And this enables a very high sensibility of the hand, as you see in this video. So this is a normal business card. And you see that as soon as we touch the card, the fingers try to wrap around the object to increase basically the number of contact points with the object. And then we tested the robustness in a bit of a savage way. So having a hammer and then hammering the fingers and see if the hand was actually functional afterwards. And well, luckily we did an evolution of this test that you will see in a moment. In this slide, I just want to show you some snapshots of the performance of the hand. So here we can grasp a very large variety of objects. So you see here some objects of the YCB database, and in the video on the top right, different objects using some combination of these primitive motions that I described before. So a net of limes or this plastic bag with salad. And here on the bottom, you see, for instance, grasping one whipped cookie. So we can also apply grasps with very low forces to avoid destroying such delicate objects. Good. Now, you saw before one rough version of the robustness test, but of course, oh, sorry, I went to her. We try to make this more systematic, and here you see the result of these tests, this benchmark. So basically, we work together with IIT in Italy, and we developed this benchmark for measuring the performance of the hand in a more suitable way using a pendulum mechanism similar to the one that is used in for testing the resilience in mechanical probes. So we were basically considering 2 different aspects: how the hand behaves under dynamic loads and the grasp resilience, or how the dynamic loads affect the hand's grasping abilities. So basically, that's this test on the top. We have a grasp object, and then we hit the object with the pendulum, and we verify if the hand can still grasp the object after the initial hit. Oh, sorry, the video is not playing for some reason. Well, but you can imagine there is the same idea of the pendulum hitting the object, and then the hand can still grasp the object. So we measure things like what we call transmissibility. So basically how much of the impact is absorbed or transferred by the hand at the base, and then the absorbed energy. Good. We also had some different way to measure the grasp performance, and this was this test from this reference, where we basically try to quantify how good the hand is to grasp an object using different approach directions. And this is visualized in these heat maps. So basically in the horizontal axis, we represent the approach direction, and in the vertical axis, we represent the orientation of the hand that you see sketched here on the left side. So basically on these heat maps, white represents very good performance of the hand, and black represents poor performance. So the idea here with these multiple maps was that we were interested in studying what happens or how the hand performs when a failure occurs. So we introduce multiple failures in the hand, for instance, a motor or a sensor failure or breaking a tendon, and then we were adopting some suitable hand compensation action once this failure was detected, and we tried to run the test and see how the performance of the hand was affected by this failure. This slide shows you the implementation of these error recovery strategies. So basically, we have some initial tests at the beginning of the operation, for instance, in the fast pull-up test or the servo pull-up tests, where we can detect very quickly if there are disconnected force sensors or the tendon is broken. During the operation, we can also do some tests. So verify as well if a tendon is broken by increasing the passive stiffness of the system. And then we compare this stiffness with the nominal and the real spring deflection. The servos can also be compared, well, measuring basically if the commanded and the real positions match within an allowed threshold. And we also check the grasp success. So basically, we adopt these hand-coded strategies to recover typical failures, the failures that we introduced, and we saw how the hand was performing. So in the figure on the right, you see the comparison of the performance. In blue is the nominal performance using only a force torque sensor or using a proximity and a force torque sensor for performing different grasping actions. And then in green, these bars show how is the performance after one of these failures. So for instance, there was one tendon that really greatly affected the performance of the hand. Good. Now at the system level, we also wanted to measure the performance of the system, of the fully integrated robotic solution. That means the arm plus the hand, plus the vision, plus the grasping planning, plus the control, while grasping and placing different fruits and vegetables. So to obtain or to make a systematic benchmark, what we did was proposing different scenarios of increased complexity depending on the level of what we call structure clutter on this logistic scenario. So you see here we have low clutter scenarios where the objects have enough distance between them and with the crate, but we can go to high clutter scenarios where the objects are very close together. And the idea is to reach this level on the last row, the real scenarios where there are multiple layers of the same type of objects coming into the warehouse. Good. So following this benchmark, we basically compared the performance of 4 different hands and grippers that we developed within this project in SOMA. And you see here actually the hands. There is the PISA IIT soft hand, then the PISA soft gripper, the Clash hand, and the robotic gripper from Technical University of Berlin. And basically here we compare different aspects, for instance, the success rate for the different scenarios that we saw before in the previous slide, and the type of failures, which is actually quite interesting. So the Clash hand is the orange bar, and actually we saw that it didn't perform as well as we expected compared to the other hands. So this was in principle a bit disappointing, of course, but we actually took this as a chance to improve the design of the hand. That's the beauty of these benchmark protocols. On the bottom figure, actually, you can see the types of failures. We classified the manipulation action in different stages, and we saw that most of the failures were happening on this grasp stage, meaning there was some problem when you were actually trying to grasp the object. But there were also some other failures, for instance, in the transportation stage, or even system failures, what they call system failures. So some failure in software or some error that was unexpected. Good. There were also some interesting things with this benchmark. So for instance, none of the systems that we tested was capable of solving this high clutter scenario. And well, there are different reasons for this, but basically solving these very cluttered scenes for the logistic domain requires a combination of different factors. So one of them is vision, for instance, and we saw that, for instance, learning-based solutions are very good for detecting instances of objects in the medium and low clutter scenarios, but several state-of-the-art algorithms cannot detect all the objects in the crate. So they can detect some of them, but obviously if you didn't detect all the objects, you cannot grasp all of them. So this was an interesting finding from this benchmark. Good. So the idea here is, of course, we need to have better vision system, and actually, well, we have been exploring different state-of-the-art solutions, even commercial solutions, and well, there are actually some solutions that now we have discovered in the last months that can deal with this type of scenarios. However, there are very challenging things like these salad bags, where differentiating where one of the bags is finishing and the other one's starting is kind of tricky. But okay, for these high clutter scenarios, you can come up with handcrafted strategies like the one that you are looking at in this video, where you introduce the finger in one of the holes between the punnets, and then you slide the finger along the edge of the punnet. You try to lift it, and then the punnet is turned 90 degrees, and then you can grasp the punnet and put it away. So of course you can do these kind of things, but the goal is to make this in a systematic way with an automated pipeline. So we created this. We were working on what we called environment-aware manipulation planning, which is basically a combination of different things. So we combine a grasp sequence planner that identifies what are the objects that are easier to grasp in a given scenario, a finger stiffness planner that exploits this capability of having variable stiffness on the hand, and a finger position planner that adjusts the finger position for these very cluttered scenes where there are very limited free spaces around the object. We implemented this, and here you can see, perhaps let me just skip to the final slide. You can see how the system performs in different scenarios with different objects. And well, the system actually performed quite well, but we also want to move towards having a more generic solution. So we still feel that the implementation that we have is very suited for this type of scenarios that we had in the benchmark, and we want to move now to more generic scenes. However, let me conclude with one more iteration on these benchmarks. So for these highly cluttered scenes, we saw that having tactile information at the fingertips is really essential. So we started to play with different tactile sensors, resistive sensors, time of flight sensors that could be fitted to the fingertip, and try to use them for solving these scenarios. And we implemented actually this for this scenario, for instance, the cucumber. We adopted a different vision pipeline here, just a watershed vision algorithm for detecting individually each one of the cucumbers. And with the information coming from the fingertips, we could actually detect things like when the cucumber is rotating inside the gripper, so that you can consider this in the transportation phase to avoid dropping the object in the meantime. And with this video, I want to show you one of the topics that we are actively working on is how to enable the system to automatically recognize these errors that happen when you are executing one action. So I'll play this again. For instance, here, this is a simple example. We try to grasp the object slides because the stiffness that we set was too low, and then it tries again, adjusts the stiffness, and then it succeeds. And with this kind of approach, we actually could solve this challenge of emptying the bin, basically. So if this is a topic of interest for you, I would love to exchange ideas about this. This is really a key topic for us right now. Good. So let me conclude the talk with some takeaway messages. One, well, variable compliance allows a very nice adaptation of the hand to different objects. And in the clash hand in particular, we can independently tune the forces and stiffness without changing the fingertip position, which is an advantage of the mechanism that we implemented on the clash hand. Then we use a variety of benchmarking protocols that actually help us to improve the design, and we are still actively using them in 2 new European projects that we just started, following up on this idea of improving the performance in logistics scenarios, both in the fruits and vegetables case and also with deformable objects nowadays. Then we have, of course, this combination of sensing and manipulation planning that help us to solve this challenging scenario, the benchmark. And there are still some different points that are open on our side to obtain a generic manipulation system, even for the solution of this system level benchmark that we were using as a guideline for this development that we had. Anyways, at the end, we definitely think that benchmarks are an effective tool to improve the performance of robotic systems. And as mentioned before, I encourage you to take a look to already published benchmarks and try to use them for advancing your work. With that, I conclude my presentation. So this is just a quick acknowledgement to the teams and the companies that participated in this project, and then my contact details. So thanks for your attention, and well, I'm happy to take some questions that you might have. Thank you very much.
I think we have time for 1 or 2 questions. Any questions from the audience for Maximo? Yeah.
How do you bake in things like damage?
How do you
think about damage?
the question is, how do you think about damage in these hardware systems during the benchmarks?
Damage in the system or in the objects that we are manipulating?
I guess when you're benchmarking your task, are you trying to optimize or like reduce damage that you're causing to the items?
As about to the items.
Oh, yeah. So this is a really nice question. Actually, that's why we developed this hand, because in logistics, well, you know, if a customer receives an object that is damaged in some way, the object is basically returned to the warehouse, and this is a huge loss of profit for the company. So the variable stiffness allows the hand to apply just the minimum force that we need for grasping the object. We basically have some object database below the manipulation planning layer that indicates if the stiffness and the force that you need to apply are low, medium, high. So we have some different thresholds. And that's the way that we are dealing with this topic right now. We actually, in one of the projects that we started, we are exploring the idea of measuring this damage that you can create on the fruit or vegetable, and try to correlate this with the force that you are applying to the object. This is a very challenging topic, mainly if you consider, for instance, fruits. Sometimes it happens that during the manipulation action, you don't see the damage. So you just grasp the object, you place it, and you don't see any evident sign of damaging the object. But turns out that it appears just after a few hours, and then the customer receives the object and is already having some marks. So this is really bad. So it's an interesting topic, and we are working on it. So hopefully on the next occasion, I can present you some initial results of this approach.
All right, thank you, Maximo. We'll move on to the next speaker.
Thank you very much, everyone.
All right, thanks, appreciate it. Kiana, do you want to share your screen?
Sure. Hopefully you can see the screen.
Yep, looks good.
Okay. So our next speaker is a recorded talk. Professor Fei-Fei Li is the Sequoia Professor in Computer Science Department at Stanford University and co-director of Stanford's Human-Centered AI Institute. Previously, she was vice president at Google and served as chief scientist at Google Cloud. We are going to listen to her talk, and unfortunately there won't be any questions for the talk, but hopefully you can email her if you have any questions.
Hi, everyone. It's really cool to be in this workshop discussing some of the latest work we're thinking about for robotic learning and training and benchmark. So the title of my talk is Simulations, Robots and Virtual Agents Towards Training and Benchmarking Human-Level Activities in Embodied AI. I wanted to start the talk by opening up our aperture a little bit, and then we're definitely going to focus on talking about benchmarking. So the world is changing really rapidly, and I'm showing you 4 so-called future applications of the related set of technology. Some of them are already here, be it virtual tutors or robotic home robots, or rescue and work assistive robots, or just this interface between physical and virtual world to bring humans experiences in AR, VR. So looking at these potential applications and the set of technologies that are empowering these applications, we're starting to see a very exciting trend is where the world of atoms and world of bits are starting to intertwine in unprecedented way. And in this, as the world of atoms and world of bits revolve each other and intertwine, we ask ourselves, what are the parallels? What are the important ingredients and technologies that needs to happen for these applications to take full shape? Well, I would say that there's quite a bit of parallel and interesting connectivity between these 2 worlds. In the world of atoms, as we know it, the most important form of intelligence is animal intelligence, especially human intelligence. We have a embodied shape, our body, and in the world of bits, we start to see a parallel story where we can imagine embodied AI as the software brain will empower, enable virtual agents and avatars in the virtual world. But the crossing is also extremely interesting, is that physical robots that operate in the world of atoms are more and more going to be powered, empowered by embodied AI algorithms, whereas virtual agents in the form of digital twins, avatars, will have interactions, will be partially driven by humans. So this is just a thought, draft picture of what we see, where the human intelligence and embodied AI in the world of atoms and bits are starting to intertwine. But in order to really fulfill the application dreams, as well as create embodied AI that truly can work as brains for robots, as well as for virtual agents, there are still quite a few big challenges remained. This is by no means to be an exhaustive list. It's just a lot of conversations and discussions going on within Stanford with my collaborators. But some of the key questions that excite us are, for example, there is a need to develop photo and physical realistic environments to develop embodied AI as we think about the virtual world. There's a need right now and a lack of it for a set of potentially accepted tasks or environments or evaluation standards to train and benchmark embodied AI and robots eventually. We still are in very early days of algorithms that can perform ecologically complex and diverse, such as human level tasks. Everybody dream of dishwashing robot, but we're pretty far from that as far as I can see. We also have questions like, how do we generate and render the body, different bodies in body AI for virtual as well as physical agents. We also are just scratching the surface in terms of understanding the collaboration between agents, whether it's between virtual agents or virtual agents and humans and robots and humans in both virtual simulated and real world. So these are, again, just a partial list of big questions that continue to excite our research agenda. But today, we're here to mostly talk about training and benchmarking. And I think there is a huge opportunity in robotic learning and embodied AI to up the game here, because without that kind of challenges and a push for that kind of North Star, it's hard to make large strides of progress. Speaking of progress, let's just get back to reality a little bit. This is a fun video to watch of, when we are dreaming of all kinds of robots helping us to wash dishes and cook meals and clean toilets. By and large, today's robots are still struggling with extremely simple tasks in an environment, a natural environment like this one. So there's a long way to go. In our field, we are seeing a lot of really exciting work happening. Most of them are still, including our own labs, are focusing on skill level tasks and short horizon goals and punchier tasks that are not composed of multiple subtasks and goals. And we recognize that a lot of our own work and work from the field are published in relatively small scale and anecdotal evaluation setup. The tasks and the environments are experimenter picked and not very standardized, and there is no agreed upon metrics. So these are all the this is not a criticism, it's just where the progress is, and there is opportunity for pushing this forward, especially recognizing real world is very different. Real world is ecologically complex, it's dynamic and uncertain. It's largely, it has large variabilities, interactive and social, and extremely multitasking. So we recognize the moment because we have seen inspirations from related fields where benchmarks and data sets, and more importantly, tasks and goals help the many of the research effort to move forward, and we call that North Star questions for different fields. And maybe there is a opportunity for pushing this North Star question for robotic learning and embodied AI. And that's what we want to share with you today, is a new work that we're presenting here at CoRL 2022, ecological robotic learning environment, and how it can enable our training and benchmarking on a large and diverse set of activities. And we call this behavior, which is benchmark for everyday household activities in virtual, interactive, ecological environments. This is work done by a fairly large group of students and collaborators. Many of them are here at CoRL. I really encourage you to find the students and talk to them about this work. So before we start showing you what are the details of our benchmark and the environment, I actually want to step back and ask the question that is very important, is what do we want to make robots for? And this question is not only asking ourselves as researchers, the whole public, the society is asking us. There's more and more awareness of the relationship between technology and our civil society, our economy. There's a lot of concerns about replacement of not only human labor, but human agency and human dignity. So when we are when we started this project, it's actually really important for us that we take a human-centered approach for defining how we want robots to help us. So let me just run a test for you, right? I know I cannot see your hands, but let's pretend you're answering these questions, at least to yourself. What kind of activities would you like robots to help you with? And I think that answer might vary given who you are and your preference in life. But let's say, what about cleaning kitchen floors? Most people find cleaning work pretty tedious and tiring and don't mind some robotic help. Shoveling snow, is another very tedious and sometimes even dangerous task. Folding laundry gets a little bit interesting. Some people actually like it. I personally like it, but it is very boring and tedious and repetitive for many others. Cooking breakfast depends, right? Cooking breakfast for your loved ones might be very fun. What if you are a fantastic chef? So this might not be a task you want robots to help. And what about opening Christmas gifts? We're about to do that. How many of you actually want a robot to open Christmas gifts for you? So maybe the answer is not too many. So the bottom line is, we want to focus on people. We're making robots or embodied AI agents to help people, not to replace people. So we took a large number of human household activities from different government data sets, and then we put together a user study of a fairly large number of people, 1,400 plus participants on Amazon Mechanical Turk. We try to diversify them as much as we could. And we asked the question, how much would you benefit if a robot did the following task for you? And the answers are really fascinating. There is a statistically varied, set of preferences. And we rank these answers and we find some patterns, such as cleaning tasks are preferred by people to get robot help, whereas a lot of entertainment and socialization and, like opening Christmas gift or playing squash or are actually preferred by humans to do it themselves. And though, and here's just another way to visualize the different clusters of tasks. But the bottom line is, we looked at this result. We picked the top 1,000 activities where the scores are high for the need for robotic help. And we're about to share with you, we built this training environment and benchmark by focusing on these 1,000 tasks that respects humans' preference. Okay, so now we have the task. The real work is, how do we build a training environment and benchmark setup? We, after getting the task and defining the task, we need to actually get the environment. We put a strong focus on ecological and diverse scenes and objects. We want the scenes to look as realistic as possible. So we actually obtained digital versions of 50 real world environments across many different scene types, like homes, offices, restaurants, schools, and so on. And these are scanned scenes, and we built a 3D environment from this. And then we also obtained more than 5,000 3D object models across 30 plus different object properties, 1,200 plus object categories. This is still ongoing work, but it's important to diversify and have this large data set of interactive and realistic objects. Now we're ready to put together a simulation environment for this training playground and benchmark playground. Simulation environment has been a really important breakthrough, I would say, in our field. They have a lot of important properties that are very useful. They're fast for training. They are safe for robots and the people and the environment. And a lot of them, it is quite a reproducible way of doing science. And frankly, you can sample infinite number of possibilities in these training environment, simulation environments. So a lot of people have been making incredibly important and useful training simulation environments for robotic learning. And here we just acknowledge a small set of work, pioneering work in this, and our own work built upon and are very much inspired by these simulation work by other members of our community. In our behavior work, we collaborated with NVIDIA's Omniverse team and created a simulation environment called OmniGibson that focuses on realism in physics, perception, and interaction. Here's an example of physical realism of different effects such as thermal effects, lighting and reflection, fluid deformability, transparency. Here is a user test on the perceptual realism by asking users to score how realistic our environments look like. And behavior environments has scored fairly high compared to other environments in terms of this perceptual realism. And of course, we strive towards interactive realism, where I'm just showing you examples of our robots able to deal with rigid, non-rigid, and fluid objects. Here's just a table summarizing another important property of behavior, which is the diversity and complexity of the tasks, building upon these realistic scenes and objects and realistic renderings and physics. We focuses on the scale as well as the ecological complexity of our activities, and try to focus on long horizon tasks that are similar to what humans perform in everyday environments. So this is just the beginning. And one important question is, what do we do with this behavior simulation environment and benchmark? Well, we hope that we can develop next generation algorithms to empower virtual agents, embodied AI, and eventually robots. But the first step towards that is actually to understand how we are doing right now. And this is ongoing work. I'm just showing you a little bit of the early work in benchmarking is using two families of algorithm. One is the soft actor and critic RL algorithm. The other one is PPO-based algorithm to see how they're doing on behavior benchmark. We selected 3 long horizon tasks: store decoration, collecting trash, and clean tables, and have used a different setting for benchmarking. The first one is providing no privileged information to the robot agent. And frankly, the model more or less fails because there's no additional information, including action primitives, and the performance is at 0. Then we relax our condition a little bit and provide some action primitives, and we can see that our model can the PPO algorithm can leverage on the privileged information and show some signaling performance. If we add on top of action primitives some memories and extra privileged information, the model performance improves as well. This is only the beginning, and it's just a small scale experiment to show you that there is a long way to go in training robotic algorithms and embodied AI algorithms to perform these long horizon tasks. And of course, in this very complex environment. And of course, the eventual goal of many of us here at this conference working in robotic learning is the real world transfer. And while behavior focuses on simulation world, we are actually paying attention to study how these algorithms can transfer. We have built a small environment in our department that has a digital twin and a physical twin as a small apartment in our lab. And here's just an example of showing you our mobile manipulation robot called Marvin has successfully performed a sequence of tasks by picking up the bottle, and it will go towards the trash bin and navigate there and put the bottle in the trash bin. This is just a very small anecdotal example to show you the kind of work in sim to real environment we're working towards. There is also a lot of failures we are, not showing, and for example, failed to picking up the bottle. Just now it was failing to navigate to the right place. Failed to place the cup in the trash bin, and so on. So all this is saying we have a long way to go. So last but not the least, I want to just finish this with a small promotional video to show you about behavior. Here you're seeing the diversity of the environments we are using, and here you're seeing the interactivity the robot, the simulation environment can enable. Here's more examples of objects. Notice the articulation and different properties. And we hope you also get to talk to our team members about this and check out our paper that's published. And last but not the least, I want to acknowledge our students and postdocs and collaborators on this project, as well as all the funding sources. Thank you so much.
As we mentioned, we don't have time for questions with Feifei. Also, there's a video. But if you have questions about that work, you should ask our co-organizer, Sanjana. She is one of the authors on Behavior 1K. So stick around after this session if you want to chat with her. So I'm going to introduce our last speaker of the day. Thank you all for being here. Our last speaker is Lydia Kavraki. She is a professor of computer science at Rice University and the director of the Ken Kennedy Institute at Rice. She receives her PhD in computer science from Stanford University. Her group produced the Open Motion Planning Library, also called OMPL, which probably everyone here knows about, but is the preeminent framework for motion planning that everyone uses. Kavraki is a fellow of ACM IEEE and has won numerous awards, including the ACM Grace Murray Hopper Award and Robotics Pioneer Award from the Robotics and Automation Society. Thank you.
Thank you. Thank you very much for your invitation. I really enjoyed this workshop so far, and I'm going to offer a different perspective. I'm not going to talk about learning, and I'm not going to talk about simulation. I think we heard a lot about this, and there is amazing work that is being done. I'm going to talk about motion planning and offer a perspective that I think bears some relevance to what the community is trying to do today with benchmarks and learning. So motion planning is a subfield in robotics. We are dealing with a very, very specific problem. This is where we started. Really, robots that it was called the piano mover problem. Remember, it was moving a piano in an environment, and you just had to make sure that this piano did not have any collisions with the environment. And then we inserted kinodynamic constraints, and we wanted to make sure that we have a plan for going from A to B without collisions, respecting all the constraints of the system. So there is a big area, and many people have worked on this, on the topic of motion planning for many years. Today, we see mainly focus on systems with high numbers of degrees of freedom, like the ones that you are showing, that I'm showing here. Look at this robot in the middle. It really goes through a narrow passage in the space, and it is a difficult motion planning problem to execute, even when you have a model of the robot and the environment. The last example on the right shows Robonaut 2, a robot that is that was built by NASA to work on the space station, a 15-degree of freedom system, moving, however, in a very confined and known environment. Still, planning for such a robot is a challenge. So in motion planning, traditionally, interesting problems include high dimensional problems. So robots with 7 degrees of freedom or more, I mean, motion planners researchers in motion planning will consider planning for a 2D, 3D robot solved. But 100 degrees of freedom is kind of interesting. And this may not be just a robot, it could be a protein. I mean, people like me have had a second career actually taking some of the techniques in motion planning and applying them to understand motion and shape of molecules. We also are interested in having constraints in the environment, so obstacles, manifold constraints. You can hear I'm showing an animation with manifold constraints, so geometric constraints. This is a problem that has 140 degrees of freedom. So all these links hold the plate, and they really need to hold it and maintain this constraint, otherwise the system will not work. Kinodynamic constraints were shown in the previous example. And the community cared about pathological environments, backtraps, narrow passages. I mean, how do you plan for these cases? How do you design algorithms that are general and plan for these cases? Classical assumptions include good models, good controllers. Often quasi-static assumption was done, full observability, and simulators are used, and they are used for propagating the system, for propagating hard to model systems, systems for which we do not have equations, like, the car that you see here was not going fast enough, couldn't get off on the ramp. And now simulator is used to understand how it gets off the ramp, but really, the visual element was never considered. I mean, it was never the goal for things to look nice, just to make sure that the physics were taken into account as best as possible. So for a very large of a set of planners, which are called sampling-based motion planners, and with which I have been involved from their inception, we start with an abstract configuration space with one dimension for each degree of freedom of the robot. The configuration space obstacles are implicitly defined, okay, by configurations in collision. So you have a collision checker that tells you if you're in collision with an obstacle in the environment or not. The problem is defined by the workspace, the start and a goal, and we are looking for a collision-free path. The general way that the sampling-based motion planners work is as follows. You sample a configuration, and somehow, and I will not go into details, you try to extend or connect new configurations, extend this configuration to new parts of the space, connect to an existing graph or a tree. And this is a very extensible and very general framework for search, as you can understand. And there have been successes. And actually, there is not one sampling-based motion planner. There are, here, I stopped counting at some point. I mean, there are hundreds, I would say, at this point. And because the way that these samples are generated, we face the problem, or how do you compare across all these different planners? So How do you compare? So let's talk about benchmarking for this particular problem. Of course, there are caveats I recognize, but I want to focus us on one thing. I want to make a point. I recognize that motion planning is just one part of the puzzle. Yes, we are talking about systems, and the assumptions that these algorithms have don't always hold in the real world. But let's look at this motion planning problem. The planning community broadly cares about generality and efficiency. How many different problems, different robots, and how quickly can this be solved? So opening a drawer, that means opening any drawer with any robot. We want an algorithm that will do that, given, of course, a model for the drawer, how it can move, and a model for the robot. Many methods, so we care about if the problems can be solved, if the algorithm generalizes without much intervention, and solves for a different robot and in different environments. And many methods also care about cost and convergence over time. What did the benchmarks include? Well, tasks, but the tasks here in this area are defined with start and goal regions. Okay, this is different from how tasks are unified and brought in learning, and fully modeled environments with interesting features like narrow passages. And when we talk about benchmarking, we talk about the use of statistical methods. So we report medians, confidence intervals, success rates, and all that. And you can see a picture here. On the x-axis are different kind of planners. On the y-axis is time. How do they perform on a particular problem? You can get an idea of which planner to use for this specific problem. The open motion library that was just mentioned was and is still an effort to systematize and compare sampling-based motion planners. It grew out of frustration because at some point there were papers that were appearing at robotics conferences, and every paper claimed that it was better than the paper before it, but it was not clear why this conclusion was made. The library was it's about 10 years old right now, but still actively maintained and used. And as I said, it provides implementations of state-of-the-art sampling-based motion planners. So by forcing a common interface, by forcing all these planners to use the same core concepts for collision checking, we can arrive to a comparison of these planners. And this is not done in OMPL, but it's done in a companion software suite, which is called Planner Arena. So in Planner Arena, you can take the planners that OMPL has. You can input your space, your problem, and it will give you back examples like this one, where you can get box plots for the performance of the planners. And there are, as I told you, several different planners, and OMPL currently has more than 60 of these planners. And if you are talking about an asymptotically optimal planner, it will give you the best cost as a function of time, because it's not only important to choose a planner that is asymptotically optimal, you probably want to choose one that has a good convergence properties for your particular problem. So this infrastructure, let's say, has been used a lot, but still, I must say that there has been significant resentment from the community. Sometimes we had requests. This is an open software, an open source library. We welcomed from the beginning contributions. People would send us their code. They would need to use the basic primitives for the library so that we can compare algorithms. And we did a code review and then incorporated the planner in the library. Many people withdrew their planners because after the planner is incorporated to the library, then you go through the benchmarking and the results were not always what they wanted to see. It has been very interesting to see that, and it happened multiple times. So the benchmarking that is done in motion planning is very different than the benchmarking that is discussed here. Many of the problems that we look at are not realistic, okay, puzzle boxes. They're hard and interesting, but they're artificial. So the assumptions are very often implicit, and it is actually implicit in learning too. For example, if you are talking about manipulation on a table, okay, tabletop manipulation, this is a very different kind of problem than going, in a building and finding into a particular room and opening a drawer. These are very, very different problems. But sometimes, and tabletop manipulation sometimes can be very easy compared to opening a drawer or picking something from a shelf. And they are not always discussed, these assumptions. The other thing is that expert knowledge is needed to understand and tune the planners. And unfortunately, many, it is hard to do, and many unavoidably use a library without this, the tuning of the planners. And different environments are needed, and variations in each of these environment is very, very important. It is a lot of care needs to be put on making conclusions about different methods. Here I have an example which is a real example you can find in our papers. This is a planner that has been run of five different variations of a problem. And if you look at this, you will go, oh, of course, I'll use the green planner, right? But if I show you the whole picture, if you do this analysis on variations of the problem, you see that at the end, the conclusion is no, the yellow planner is what I should be using and not the green planner. But it's hard to get to this kind of analysis, even for a very specific problem. I talked to you about a motion planning problem that has a lot of constraints. We have, as a group, done a number of things to address some of the difficulties. I'll discuss two of them: the expert knowledge that is needed to understand and tune the planners. Okay, this is something we've run to many, many times. OMPL, for example, has some default parameters that honestly students in the lab found they worked, and they set these planners. But if you are going to use this planner, you should not be relying on these standard parameters. You don't need to do that by hand. I mean, now we have a software which is called Hyperplan, and really it uses techniques for learning. This is a hyperparameter optimization that you're doing, and you're applying them to planning. So the Hyperplan using a Bayesian optimization and hyperband, and it can produce order of magnitude speed up over the default parameters of OMPL. So if you are using one of the motion planning algorithms, at least make a minimal effort to tune the planner. And typically we use all these planners with octomaps now, not geometric models, but octomap models from of the environments. And I'm not showing you the details. You can find them in the paper, which was at IROS last year, but it's a huge improvement. Okay, the baseline, which is the standard parameters of the planners, look at the amount of time you're taking, and this is what you get after using Hyperplan. So at least do a best effort to use the planner correctly, so that the comparisons that you're going to make between different planners, among different planners, are trustworthy. And it can be done automatically. I mean, you don't really need to hand tune the planners. The second thing, the different environments that are needed and the variation in each environment are very important for understanding what kind of planner you're going to use. And remember, I'm still talking about a much simpler problem than what has been discussed here in this workshop. So in order to run motion planning with different environments and have the ability to work with MoveIt and to execute it to a real robot, you need a lot of, let's say, machinery. And one of the machinery that we are offering right now is RoboFlex, which is really a wrapper. It's MoveIt made easy. I mean, this is the shorthand for RoboFlex. It makes it easy to copy, modify, collect environments from simulation or real data. So that when you are going to evaluate a motion planner, you are going to evaluate it on different environments and slight variations of these environments. And this is, I think, why this is one of the things that the organizers of this workshop asked me to talk about, the motion benchmaker, which is a suite which is a tool to generate and benchmark benchmark motion planning data sets. This a robot benchmarker takes in as input a robot description and a scene description. And what it does is that it samples the scene and creates a set of scenes that are around the original scene. It contains, so it's a systematized, a procedural way of generating benchmarks. It has a problem generator that is agnostic to the robot that you're going to use. And it has also an octomap generator so that in the end you can use an octomap of the scene and plan using the octomap. This work was published at Robotics Automation Letters and was also presented at ICRE this year. Generating problems with variation, as I showed you before, is very important for us, and the plans do change a lot, even with small variations. So you need to understand what is the average performance of your planner. If the figure of the right, the robot was getting to the obstacle from the left. Here it's getting from the right side. I mean, this is yet another way of reaching the end effector to a particular pose. And this all can be generated, these problem variations can be generated automatically by OMPL. So robot benchmaker, so that you can have the same problem, let's say, but you can have different robots that deal with the same this problem. And usually manipulation is something that presents more difficult examples, more difficult benchmarks for motion planners. So these are some of the kind of benchmarks that we generate from the same nominal scene, changing the scene. We sample the positions of the objects in the scene, but also URDF constraints so that we can have kinematic constraints like opening drawers and boxes and things like that. So here is a predefined set of interesting problems for robot motion planning. I'm not claiming that this is the answer to benchmarking for motion planning, but I want to tell you that it took about 20 years to get here because there was not agreement in the community about what to benchmark and how to do it. And it took also collaboration between 3 different groups: my group, Mark Toussaint's group, and Mike Glaciers group at Wisconsin to get to this. So if you're getting into this endeavor, it is a lot of work and a lot of thought that needs to be put on how to do things. And now modern motion planning techniques really, are not covered by what I just said. I mean, now we want to plan under uncertainty in dynamic environments. We want replanning. We want planning for long horizon tasks. They don't share the assumptions that I talked about that created, let's say, a motion benchmaker. So geometric constraints, I want to talk a little bit about manipulation planning, and I will finish with that. So manipulation planning for somebody like me means that you get the state of the environment from, let's say, state A to state B, which may mean a number of short motion plans that need to be stitched together in order for something to work. And you saw here one example, which we called multimodal planning. So you have to understand where to grasp and how to grasp, and how to move the object from an initial to a goal configuration. And here you can see a more complex task, which is you need to specify what the task is somehow, which is to move the stack these 2 objects. But first you have to clean the table. So you have to find a way to specify the task. You have to find a way to understand what operations you need to do and how to sequence them. And there are 2 things here. There is the discrete part and there is the continuous part, the motion planning part. The discrete part can be fairly complex, and sometimes let me start from the geometry, which is easier to explain. The geometry, you may want to do something, but you cannot do it. Okay, it may not be feasible. It would have helped your task, but it's not feasible. So you have to think about what to do with a discrete part of the task so that each of the steps that you need to execute actually can be executed by a robot. So it is something that we've been working on for several years. We call it a task and motion planning. Some of us call it task and motion planning. Some call it multimodal planning. And there are methods that solve, and these are methods that solve these bigger, more realistic problems that we want to get at. There is additional complexity in connecting abstractions, the actions and the tasks to the geometry, grasp placements and motions. And I didn't hear anything about these topics during this workshop. So there is a long way to go, I think, for understanding how to represent all these things. And this is part of the difficulty. And maybe as it was discussed during the debate, it will lead us to more interesting problems, to understanding what are the problems that we are interested in solving before we get to create benchmarks and solve them. Our experience has been that for task and motion planning, which is a topic I've been working on for the last, I would say, 5 to 6 years, almost every method that exists in the motion planning community picks slightly different set of assumptions. So they relax something, every group relaxes a different thing. So we have different samplers, the definitions are a little bit different, the models are a little bit different, discretization is done a little bit differently, and it's impossible to compare. In 2017, we had been having a series of workshops at RSS, the Robots, Science and Systems Conference on task and motion planning. And in 2017, we decided, okay, let's talk about benchmarks. And we brought the community together and we said, all right, we need some task and motion planning benchmarks. And there is a paper and there is still a website that came out of this work. In my opinion, this effort failed. It's unclear what benchmarking means for manipulation planning, and it failed for many reasons. Some were technical, there is not a uniform format for specifying this problem. Some were actually the fact that it's such a broad area. When we started understanding all the different assumptions that the different groups were making when they contributed the benchmarks, and other groups started pointing them out, these benchmarks were never updated. The groups did not have the will to update the benchmarks because this, did not really help their work. And it's also a lack of scope. What is the scope that you want to these problems to capture, the task and motion planning to capture? Again, not clear, and I think it is interesting to think about this problem. In October, we had a kind of a similar workshop at IROS, talking about evaluating planning performance. And what we wanted to discuss, and we discussed what are appropriate comparisons between learning methods and algorithmic methods, which is what I'm discussing here. And there is really not an agreement on what are the baselines, what are the configurations, what are the data sets. Are the problems and the tasks the same? Sometimes we see a learning method being compared with an algorithmic method, but is the problem the same? Are they comparing for the same problem? What metrics to report is also very interesting. What is success? I'm still not clear what is success. Also something else that came out of this workshop, which is relevant as we move to robots and learning in the real world, is that diverse motion planning applications require diverse metrics. So it's a different thing to do manipulation on the table. It's a different benchmark is needed for social navigation, where social norms need to be respected. A different set is needed for multi-robot coordination, for example. For surgical robotics, safety is an issue. It's a totally different set of things that are needed. And I'm afraid that I have to say that these fields don't agree on specific benchmarks, but I think that what we can do as a community is that agree on the motivation and the interpretation of benchmarking. And moving forward, I think there is a lot of room for meaningful and insightful comparisons across motion planning, task and motion planning, and learning. These fields have different priorities, but can learn from each other. We need to understand what is the shared space of evaluation methods, and also a better communication of the assumptions and the properties made in each of these field. Shared and interoperable tools for benchmarking, datasets, and evaluation methods will of course help. So I told you what is the motion planning benchmaker, and that there was an effort by 3 groups and we got to something. But honestly, I have no idea how to get to a manipulation planning benchmaker. Okay, how to create manipulation planning benchmarks. What robotics tasks are interesting in general, what robotics tasks are interesting to both learning and planning communities. I feel there is an intersection, but I don't think we've pinned it down. And what are specification, of course, shared specification formats that will help us get to an understanding of where we are as a field, and also how to combine the learning and the planning communities. And I will stop here, and thank you all for your attention just before lunch. Thank you for staying. Thank you. I'm happy to take questions. Okay.
I think one thing that was really interesting you mentioned was about tuning the parameters for motion planners for a lot of these benchmarks. Do you see that's something that should always be done? And if so, how do you, is there a sense of I want to tune on some subset of paths and evaluate other paths, or do you always should tune the parameters for the benchmark path?
Well, first of all, for sampling-based motion planners, you should always tune the parameters. I mean, you just cannot use these planners out of the box without any help. And you should tune the parameters for the set of problems that you're interested in doing. You don't have to do this manually. As I told you, there are a set of tools for doing it, but I think this is something that has to be done. Now, with the learning, for example, if the learning is looking at a certain set of problems, you know, these problems can be used to also tune motion planners, and then, you know, you could have some kind of an understanding on what each of these fields can do. Yes.
I love the last question. You don't know how to start a manipulation benchmark. You have tremendous history on trying to figure out how to work together on these problems in the past from motion planning. Have an intuition about how to get started.
Well, I would like to get started. I don't have, I think there needs to be an understanding of what are the priorities of the different fields that are contributing to manipulation planning at this point, because each of these fields has different priorities, and that's actually good. Okay, that's not a minus, that's a huge plus. But there needs to be an understanding what are these different priorities, and I think we need to modulate to create modules. I think this is a problem for which we cannot go for one approach for everything, but we need to exploit modularity. And there is a lot of modularity in this problem. And certain techniques are better for certain modules than others. So establishing a common language and understanding what are the different priorities, because now everybody is trying to do everything. And I don't know how far we can go with that, is important.
We have kind of engineering modularities that we have.
Yes.
In don't correspond to the actual task we're trying to solve. And if we can look at the ways that we're working in common modularities, we can find ways to work together.
Yes. It's one way to go.
Can I ask one question? Early in the talk, you were talking about how motion planning was, especially sampling-based motion planning, was never designed to look good. Like it was designed to satisfy these geometric constraints, but not necessarily like the motion. But I guess what I'm wondering is, as robots enter the real world and like are interacting, we want to have them interact with people, especially like manipulation settings, like that. Do you think there is a space for sampling-based planners to like look good? I guess by look good, I mean like be legible.
Yes, so I think yes, and actually the original planners, for the original planners, there was no notion of it has to be a nice motion. At that point, there was no solution. So we went from not being able to solve the problems to having a solution. But nobody said that you should be using these planners that were developed 20 years ago for the problems that we need today, where we care about the quality of the path. There are sampling-based planners, asymptotically planners, and optimization-based planners that can be used. They are just far more complex. All right, you pay something, okay, and the original plans were really simple. They did the job. They did a poor job. Okay, but they solve the problem. If you want to use motion planning in today's context, you need to go to these more complex planners. But for these more complex planners that are in OMPL, and we can talk about it, you need to tune them. So you need to understand what is it that these planners are doing and why are they doing it and how do you tune them? If you don't do it and you don't spend the time, well, that makes no sense. You see, so there are many different planners. There are some that are very fast, very simple. They help the community really move forward. But this doesn't mean that today we should be using the initial versions of these planners. They're far more interesting planners, but you have to pay somewhere, okay? You pay in the complexity of the planner and you need a more mature understanding of the problem. Right, but these planners are available and the community is not using them. Why? Because you need this extra understanding, and that's why we are trying to give you through the hybrid plan and through the tools that we have developed an understanding of what is it that you should be using. I am very frustrated sometimes when I see comparisons with planners that were developed 20 years ago. The moment that there's so much better methods that can be used today. And if there is at some point a connection of the learning community with the motion planning community, if planners are used to create benchmarks for learning, it would be really sad to see these original planners being used because they do not provide the quality of paths that we need today. The same for manipulation planning. If we are going to have a connection between learning and planning in that context, we have to go with the right planners.
So if someone today wanted to do that, like, okay, I want to go out, I want to make a benchmark set, and I want.
For what?
For like, right, that's a good question. I guess it's the whole point of the problem.
Mm-hmm.
But so I shouldn't just ignore that. But for some manipulation task, like task X, I don't know what the task is right now, but how should this person go about choosing which one of these planners? Like, do they go to the OMPL website? Is that the place to start?
That is one way to start, yes. Mm-hmm. And if you go there, you'll see the planners that are there, the evaluation tools. You see pointers to other software that is offering different options. But yes, work needs to be put in choosing a planner. You cannot just choose, a random, an easy planner, maybe the ones that they're used a lot because they're very simple. They're simple to implement. I mean, there's a real power in it. Okay, this is really very, very good. It helped the community tremendously. But now we have to go past these planners and use what is appropriate for the problem that we need, that we have to solve. Yes.
Given that we identified this mismatch in different academic communities,
yes,
how they approach the problems, do you see an opportunity for the industry to perhaps drive some of these challenges? And,
yes.
Is it also dangerous, perhaps over focus on specific tasks?
On specific tasks, right? Focus on specific tasks. Yes, I think it is dangerous to focus on specific tasks, and if you're also a good person to answer this question, but if we focus, if we go too much down on one category of tasks, with learning, for example, we are, I think, going to lose this idea of generalizability that exists in the motion planning community. So a partial answer to the question. Grasp it. Mhm.
There's these sort of assumptions which can apply.
Mhm. Yes, absolutely. And you should be using the singular solution. You should be using the singular solution. That's why I'm saying, I mean, the comment I made it before is that, I mean, we cannot be stuck with planners that were developed 20 years ago because they were fast, because now there are simpler solutions. Sometimes it could be an optimization-based planner that is good, or a planner that, you know, maintains contact. Okay, yes, these are the solutions that need to be used. Yes, I agree with you 100%. Yeah. Assumptions, yes. Yes. Yes, yes, I see your point, and I hope this collaborates my discussion on how difficult, even for this problem, it has been to create benchmarks. And also that maybe we won't get to a benchmark, you know, for everything. But what we could do is understand, I mean, have an understanding of what is it that we want to do with a measure, with a benchmark, and an understanding of the goal. What is the goal that we have with the benchmark, and some agreement on the methodology and the assumptions that are made. I would be happy to take discussions offline because we are now in the lunch time. Okay, thank you very much.
Yeah, I guess, yeah, thanks everyone for coming. I mean, yeah, it's kind of late into lunch, so I don't want like too long, but yeah, thank you all for coming. I think there were a lot of interesting discussion points, a super spirited debate. Thank you to all our speakers and panelists, and also our co-organizers, particularly Clemens and Aditya and Kiana, who couldn't be here today. Yeah, thank you. Thank you.
Thanks. That's what happens.